Game on. Oh, I probably should have put the slide up before I started. Just checking that everyone can hear me. I will set this to presentation mode. I apologize. I think is that Korean text. I don't know how to pronounce your name there. But the question was about, are the help sessions related to the lab questions? The help sessions are actually for you, so they can be related to whatever you would like to ask. If you want to go to a help session to ask about anything to do with the course, you can ask anything to do with the course. So you can go to a help session and ask about lab questions. You can also go to a help session and ask about assignment questions. You can even go to a help session and ask about the optimal way to configure your computer to work with something like COMP1511 and things. So there's not really any limits on what you can ask in a help session. Well, I mean, as long as it's related to the course. If you go to a help session and ask how to bake a cake, well, you might have an interesting conversation depending on which tutor you get. But yeah. But if it's anything to do with the course, you can ask in a help session. Michael's talking about playing around with challenge exercises. Um, oh, and Matthew's making fun of me for using Google Slides. I like Google Slides because they're very oh yeah, sure, the layout's not amazing or anything like that, but I mean, like, you're not here for my slides layouts, you're obviously here for my cat. Um, but I just like it because it's like one of those things that's really safe. I should talk about this. It's always a nice thing when someone reminds me of something that I can talk about. I used to do this thing where I would work with students much more closely. That was before I had 700 of you at a time. When I was working at the same kind of capacity that your tutors are working at, in a different kind of form of education. But I used to say to my students that I would never accept I've lost my code as a reason why they couldn't submit an assignment. So I was never going to accept that. But in order to have that kind of a hard requirement, I always teach them that you need to make sure that anything you're working on is backed up in 3 physical locations. And I say physical locations because what you want is any kind of mistake or mishap that happens to your code, you want to make sure that it's in more than one place so that if something goes wrong, you don't lose it. So for example, if the slides are only on my laptop here, it's really, really volatile and really unsafe. I can have a single hard drive failure, or just the laptop failure, and then suddenly I can't deliver my lectures, which would be, I think, unacceptable. I have to deliver these lectures no matter what. I've got hundreds of people wanting to see these lectures. 2 physical locations might be I've got 1 copy at CSE and I've got 1 copy on me. That's not too bad. That's pretty good. There is a very, very small chance that both my computer and CSE fail at the same time, which is possible if I happen to be there with my computer, and the building catches fire, and I am not necessarily going to try to lug a computer out if I'm running away from fire. So that means that the 2 physical locations is a little bit risky still. But a 3rd physical location, let's say my stuff is on Google Slides, so it's in California. I don't know if that's where the data center is. I'm sure they've got an Australian data center. But either way, it's really hard to burn down 3 buildings at once. I'm sure someone's tried. Don't try. But yeah, but I'm really safe like that. I had a friend who had a really, really funny approach to backups. Once a month, he would go to his grandmother's house, which is like separate from his own apartment, separate from his place of work, and he'd bury a USB drive there. So he would regularly put all the stuff that he thought was important on a USB drive, and then bury it in his grandmother's backyard. And it was so safe because it was buried in his grandmother's backyard that even if her house burnt down, or there was like a big calamity like that, he would still have his 1 month ago data backup. So yeah, that's the thing I say. If you think something's important to you, 3 physical locations. So don't think about necessarily the virtual locations unless you're sure the cloud storage you're using is not in the same building as you. I mean, you can be pretty sure of that right now, but when you are working on the CSE labs, you kind of will have the idea that the storage for the CC labs might actually be in the same building as the labs themselves. I can't remember if our storage is actually in K17. I think it might not be, but I'm not sure. So if I'm not sure, then I'm going to make sure I've got some storage somewhere else that my stuff is saved. It's good to have that kind of thing. At least you know that we're backing up your stuff in multiple locations if you work on your CSE account. So there is actually a way to restore backups if you accidentally delete something or lose something on your in your COMP1511 directory, especially because we're not just teaching you programming, we're throwing you into a new operating system. And if we're throwing you into a new operating system, we do expect that sometimes people are going to delete stuff without knowing. Which is why in the first lectures it was like, okay, here are the commands to move things around. This is the command to delete stuff, RM. I always like to make the BTS reference when I say RM. It just makes me laugh. But you got to be careful with that one, right? Because if you remove something, that's deleting it, and then you've got an issue, and you might lose it. So always like to say that 3 physical locations is the best way to back things up. Let's see what everyone else is saying. I don't know why I reacted to Matthew making fun of my Google Slides, but I think it's like, there's this instinctive thing as a teacher where I'm just like, oh, I can teach something about that. I'm going to take his insult on my slides and I'm going to teach him something. That'll teach you. Someone is saying that my microphone is a bit quiet. Someone else is saying the sound is good. I'm looking at my output there, it is maybe a little bit quiet. Let me just... Where is its audio properties? Sound mixer options? No, it's input devices. Now you know what brand of webcam I'm using. Where did that go? No, I don't want to disable it. Output, input, test my microphone, device properties. That's the one I was looking for. There you go. It wasn't on 100. So you were right. It was a bit quieter than normal. And now I can see my meters are going higher. Okay. Thank you for letting me know. That's handy. Okay, let's just see if there's anything else before I kick off what we're talking about. We're talking about baking cakes. Eric is saying, are we allowed to make variables like counter equals 0 in the assignment? Definitely. I'm pretty sure you're not going to be able to do the assignment if you don't have some variables. So you're definitely going to be wanting to make your own variables. Austin is asking if we can use structs in the assignment. I haven't taught you structs, so if anyone else is wondering what a struct is, you don't need them. So you don't need them. If you really want to, you can use them. They're legal C, and we are going to teach you about them. But since we haven't gone through the subtlety of what they are and how they work, I would be careful, because if you are going to use them, we're probably going to mark them based on what our criteria for marking them would be, which we haven't taught you yet. So it's potentially dangerous. I can see some points where I might use them because they're a little bit, they can neaten things up a bit, but I would be careful with that. If I was going to use something like structs, if you're someone who's going to use structs, it's obviously you're someone who has learned a bit more about programming. I would get the assignment finished early and take it to your tutor and talk to them about it and say, look, I used this thing. Mark warned me about using this, so can you look at this for me and just give me some advice on whether I have done this the way that Mark will be expecting of us. I'm wondering if I'm going to have taught structs by the time the due date comes up. If I have taught structs by the time the due date comes up, then it's much less risky to do it, because then you'll actually see how I teach it and things, and then you'll have some pointers on how I think it ought to be done. Do I believe the phrase good artists borrow, great artists steal? That is not a question I'm going to answer here in the lecture. I am an artist in my secret other life, and I've gotten a lot from replicating other people's work. Whether that's actually stealing or not, or just learning from people, I think that's the inspiration behind that quote, is learn from other people. So I said to someone once when I was marking their assignment, I said, your code style looks exactly like mine. It's like looking in a mirror. And then they said to me, well, that's a huge compliment. I didn't realize it was a compliment. because I don't consider my code style to be like this gold standard, but then I realize it has become that because I've been teaching, so I'm really careful to make my code style really good. And they had said, look, I just did exactly what you did with everything for style. And it's like, wow, it looks really readable. It's like, of course it looks readable to me because it's a replication of mine. But then their tutor gave them 20 out of 20 for style. So I was like, okay, all right. I must be following the style guide, and if they're following me, that sort of works. Alright, other conversations are happening. Oh, Michael's wondering about getting your code from VLab to your computer and stuff like that. So I think SCP is one way of doing that. That's secure copy, but I'm not sure exactly how the best way is to transfer it to your computer yourself. I think someone that does this a lot more will know. Talk to your tutor about that, because I think SCP is just between can be used for between accounts and things like that. I mean, the really dumb way would be to open up a browser in there and then email it to yourself, or open up a browser and use something like a Google Drive, or even better, set up your own Git repository. Make it private though, because if you make it public, it's potential plagiarism. Like seriously, because anyone can just find your repo and just download your code. But you could upload things to some kind of cloud storage. Git is a good one for that. Anyway, let's move on. Can we access VLab using a USB? I'm not sure. I'm not sure exactly what you mean by using a USB that way. Oh, you may be joking with a Mission Impossible movie idea? I'm not sure. And Mason is saying, yes, all you need is the USB that you bury to have wireless connectivity, and then you'll never need to unbury them. Although, the whole point of the physical backup, sometimes you want to air gap that backup so that it can't be connected to wirelessly, so then it's really safe. Anyway, water-resistant USBs, yes, people are talking about, okay, so, Reese is asking if you can delete the lab files after submitting. Yes, you can. The submission is something that copies the files over. Alright, Dean's in chat now, and Dean's answering questions. So I'm going to go ahead and start talking about what we're talking about today. First up, I left it in my slides again. This is exactly the same as me continually saying good morning all the time, even when we have an afternoon lecture. And I'm going to keep saying yesterday for the last time. Because Wednesday doesn't exist for me. Obviously, I'm on ice on Wednesdays. That came out really bad. I don't take drugs. They freeze me in carbonite when I'm not teaching, because I'm not necessary at those times. Or they power me down. It depends whether I'm a clone or a robot. You can use your own narrative for that. Okay, we talked about functions and libraries. So we'd talked about functions previously. Separate code that we can push out somewhere else and we can just call it by name. But now we started thinking about, it's not just our own code that we've written that we can call functions from other places. We had a quick look at scanf and some of the subtleties of scanf there. That's not the only one, obviously. I showed a slide that had the absolute value in it as well. I can't remember whether there was something else in that slide, but anyway, the C standard libraries have a lot of functions in them. You don't need to use them all, you don't need to learn them all. This is the kind of knowledge that you will pick up over time. So it's kind of like in the beginning, as a carpenter, I would teach you, I don't know, how to use a hammer and nails. I don't actually know this is what you learn as a carpenter, I'm just making up the idea. Teach you how to use a hammer and nail to join things together. That's one tool. You put it in your toolbox. That's like me saying printf, scanf. And then I say, ooh, there's this maths library, and that does these other things. So that's the first time that I give you a drill. And it's like, okay, here's a different tool. Someone else has made this tool. You don't even know how to make this tool. You're just going to use it. And the math library is able to do certain things. So like I can give you a drill and you go, oh, I could attach wood to each other with screws now, because I could drill a hole and then I could use the same drill to drill a screw into it. And that's like me saying, if I give you this maths library, then you don't have to try to manually do square roots or something. It's like, that's an awkward thing to do. Or I give you the C standard library, and you don't manually have to do absolute value or anything. You instead just let someone else who's made the tool for you do it. And then that tool becomes part of your toolbox, and it's more of an abstract concept here. It's not a physical toolbox, but it's the stuff that you remember that you can carry around and you can reuse. And that's one of the best things about libraries. A lot of people who have been programming for a while have big toolboxes that they carry around with them. Some people have written their own libraries, and they just carry these libraries around with them. And they say, I remember I worked on something in a previous project that could help us here. And then this could be a library that I'll reuse. Later on in the course, we're going to be building our own data structures. You know, like we had an array with lots of stuff in it? We're going to be building our own data structures with different types of stuff in it. We could make those into libraries, and we could say, well, I could use this in any program that I want to use these weird data structures that I've created. And so we can build our own libraries and use them. We're going to talk about that later, because that's very fiddly, and we've got a lot more of the basics to cover before we're going to get to that. We also talked about multi-dimensional arrays. We talked about the idea of putting an array inside another array. So an array is a container of multiple of the same variable. And if an array contains multiple arrays, we end up with like a two-dimensional space of arrays. So there's an array of doubles, and then an array of arrays of doubles gives me like this big multiple of arrays. I've got some slides on these anyway. Today, we are continuing some of the work that we started last week about... Last week I talked about the theory of computers, and we were talking about there's the CPU, which is the processing bit, and there's the memory, which is the bit that stores all the ones and zeros that we work on. And they're very closely intertwined, right? Because everything our CPU is doing is usually going to be recording something into memory, or it's going to be reading something from memory, processing something, and then writing something back to memory. You know, it's a simple concept of what it's going to do that just gets more complex the more we try to push it into doing other things. Today, instead of thinking of our variables being just somewhere in memory, we're going to look at exactly where in memory they are. So like now we get one level deeper where we can see the memory itself and we can access the memory itself, and that's going to be using these things called pointers. I'm going to talk about, well, there's a lot of detail in this, and so I'm going to try to take you through it. This is the point where the course gets hard. So I mean, like, programming's not easy anyway, right? Nothing we've done has been that easy. But the reason why pointers get hard is because they're a weird concept to wrap your mind around, because they are not just variables store information. They are a variable type that stores information specifically about another variable. So we're at this like meta level where we're not even talking about variables, we're talking about things that look at other variables. So that's one thing to wrap our head around. The other thing to wrap our head around is the fact that pointers have syntax with little symbols. So they use like just symbols on the keyboard rather than words, and so I always find they're a little harder to think about because they use those symbols. Those things need to be practiced and memorized. So the abstract part of it is the thing that you need to just wrap your head around. That can take time. The symbols part is something that just takes time. It takes time before you recognize exactly how they're going to work. So the more times you try it and practice it, the more times you go over exactly what things mean, the better you'll get at it. I'm never really going to give you advice that says spend less time on something. I'm always going to say the more time you spend on stuff, the more you're going to pick up. So this is not necessarily new advice from me, but pointers are something that are going to be reasonably important. The other thing that I say with this is that, yes, it does take a lot of time to learn. That also means that for some people it's not going to click very quickly. And I wouldn't be too worried about that. I always like to use this example. I've got a few friends who I studied with, and I remember, I think it took me about 6 months from the first time I saw pointers to start actually using them correctly. So if you think about it like that, I somehow made it through my first computing course without understanding this subject properly. I understood it just enough to get marks, but not quite enough to really think I had control over them. And that's fine. And in an introductory course, having full control over the concepts is a difficult thing. And so some people might be able to get there, some people won't. That doesn't mean you fail the course. It means you don't have full control over it, but you're on your way there. And I've got friends. I had a friend like took him like a year and a half, I think, to really grok what pointers were. And just be like, oh, is that how they work? And it's like, yeah, that was first year, man. It's like, yeah, but you know, the funny thing about him is he works for Microsoft now, and he's like, you know, I think he's been there for like 5 or 6 years. He bounced around other companies before then and stuff, and so he's a fully fledged software engineer and things, and you can do that. So I think one of the things I will say, and I've said this before about computing in general, but here is like a point where I'm about to ramp up the difficulty. If this doesn't click for you immediately, that's not a death sentence. That just means that you might need some more time. So please try not to put too much pressure on yourself to understand things immediately upon me first teaching you. There's police going by outside. I don't know if that goes through the microphone, but I'm sure it does. Yeah, so as I go through this concept, you may think that some of this stuff isn't entirely working for you. Don't worry, let it simmer. Come back in a couple of days and watch the recording again and see if it clicks better, or go do the tute, listen to the way the tutors demonstrate it, and then go back again. You know, those kinds of techniques will get you a difficult topic going, rather than necessarily trying to put pressure on yourself to have to know it the second I talk about it. So, I mean, I think that's general advice for learning in university, because university teaching is always dense. I will only teach you for 4 hours a week, and I will give you a new topic every 2 hours, or even worse, some lectures I will give you 2 new topics in a 2-hour block, and so I'm not expecting you to fully understand them, which is why you get for some of you, depending on when your tute is, sometimes you've got a week or more for the lecture to just simmer in your brain before you actually go into the tutorial and then try to bring it back up and use it and learn it. So yeah. Alright, so a little recap of what we're doing. I've kind of talked about this already, but I've got some slides on it anyway. So libraries. We use libraries with our code using the hash include keyword. That hash include is going to tell our compiler, please grab this library and basically copy and paste this library file here. You can see it's got a .h. That's actually a file. We're going to make .h's, but not yet. Later on in the course. We're going to stick to one file for now. We don't need that complexity yet until we've covered a few other things. But it's basically grabbing that file and copy pasting it into your file. It's not necessarily doing that, but you can think of it that way, and you won't be entirely incorrect with how it functions. So if it copy pastes that thing and that thing's got its own functions, it's going to be able to compile all those functions first, so that when you call a function like something like printf or scanf, it already knows what those things are. And so you don't need to have this file anywhere. Your compiler has basically a recent copy of this file that it uses for these kinds of things. We're going to use some library stuff today. I've got an example today. Today's example also hopefully will, I think, which was it? Oh no, I was going to say it might help for the assignment. It might actually help a bit for the assignment, because we're going to be using functions and stuff like that. But we're also going to be using pointers, so may or may not. We don't need pointers for the assignment, by the way. Should also remind everyone, in about 24 hours, tomorrow afternoon, I'm going to be doing a live stream about the assignment. It's a bit different from the lecture. I don't have a big bulk of content that I'm going to go through, and I'm just going to deliver. You know, it's not just all one-way communication, because the lectures is very one-way. It's me talking to you and you listening. And I know people are chatting and they're getting answers from Dean and stuff there, but at the same time, it's really just sort of one way. Whereas the live stream is going to be a bit more two-way, where I'm going to go back and forth with you and talk to you about things. Multi-dimensional arrays within arrays. I've spoken about this already, but here's a diagram that makes it a little bit easier to see. If we have an array that has rows in it, and each row has a certain number of columns in it, it's going to look a little bit like this. Your first assignment gives you a lot of practice with this. We also have some practice for this kind of stuff in the tutorials and labs. I think it's this week we've already got two-dimensional arrays in. Oh, no, we don't, because we only just taught it. So there'll be some 2D array stuff next week. Alright, accessing the 2D arrays is very similar to accessing the 1D array, except we have a second set of brackets. So if we have rows and columns, it would be the first one's rows, the second one's columns. But as we discussed last time, the idea that one of them is rows and the other is columns is something that we make up. So you need to decide how your 2D array is going to work, but stick consistent to that. I suggest that the first number is rows and the second number is columns, because then if you print out a loop, it's much easier to loop that way. If you loop the other way, things get a little bit awkward and it's hard to actually print these out, just because when we're printing to terminal, it goes across rows, and then it goes down to the next row, and then it goes across and down to the next, right? So if it's not doing that, then it's hard to loop through, because if you've got columns and then the rows in the columns, you can't loop downwards in the terminal and go back up and then write text next to it. So it's much easier to write across the lines in the terminal, which is why we do rows and columns. It's a very, very traditional kind of computing thing to go across the lines and then down each time and do it. I was talking about how our monitors work and how our monitors render the pixels out to the screen one at a time like that. It's the same kind of thing. So we're sticking to the concept that brings us closer to the machine. Yeah. Okay. So today we're going to talk about memory. And we talked about addressing as well, but this is something that I'm now going to talk about. And I want to bring in this analogy that our memory is like a neighborhood, or it's like an apartment block. I think that's like, who the hell lives on a house in a street anymore these days? But if you think of it as houses on a street, that works. If you think about it as apartments along corridors, that also works. So the idea is that every house or every apartment is a piece of memory. The standard size piece of memory that we use nowadays, I think it's either 32 or 64 bits of memory. It depends on your operating system. Which means that every house contains a certain amount of information. It's not always going to be exactly the same size as variables. Variables can go across multiple houses if we need them to. But the trick is, every house has an address. In the same way in the real world, if I was to tell you an address like, I don't know, 1000 Anzac Parade, I'm trying not to give you a real address, because the first real address I'll give you is my own house, just on instinct, and I don't necessarily want all of you turning up to my house and going, hey Mark, how do I do this in COMP1511? I have accidentally gotten on the bus with students before, and I think one of the funniest things was sitting behind two people discussing how their assignment was in stages, and this particular stage was really hard and they didn't know how to do it, and I was like, assignment in stages? That's out right now. And I just leaned over and I just went, is that COMP1511? And people lost their minds. It was pretty funny. It's the worst thing you want, is like you're complaining about the assignment, and the person that wrote it is sitting right behind you. Anyway, if I want to get to 1000 Anzac Parade, I've got an idea about how I want to get there. On my computer, I have a similar thing. Every piece of memory has an address. It's a bit simpler than say 1000 Anzac Parade, because we don't have all of this like messiness of reality to deal with. We can actually address memory just with a number. And this is really, really similar to how we use arrays. This is why I'm piecing together. Like, this is the way I like to teach, is I give you bits and pieces, and then I show you how all the bits and pieces fit together. Strangely enough, I didn't learn that in lecturing school. There's no such thing as lecturing school. I learned that from reading a lot of novels. So this is the funny thing, is you can learn stuff from all kinds of places. A lot of novels, I used to read someone called Neil Stevenson a lot. You should check him out if you like your tech stuff, because he's one of the sort of famous cyberpunk writers of maybe a decade or two ago. He's still writing some stuff now, but he doesn't write as much cyberpunk anymore as he used to. He would put like multiple different characters in, and then by the end of the story, all of their stuff would be intertwined, and you'd understand because you'd seen their separate stories and how they fit together. So I like to teach like that. Sometimes I would drop threads here and there, knowing that I'm going to pick them up later, and then you're going to get it. So here we are getting the culmination of me talking about what the theory of the computer is. I've been dropping hints the whole time about what memory is. I showed you an AND on scanf. We're going to talk about that today as well. And this is how we can actually use the idea of what we've got in arrays, where every element of the array has an index. Every piece of memory on our computer also has an index. So if we want to, we can think of our whole computer, our whole computer's memory. So everything that our program can store information in as a big array is just an array, and we can access parts of those arrays. The trick we're going to do, though, is instead of using just an integer to store the index into the array that we're going to use, we're going to use a specific addressing mechanic to find things, and that's a thing called a pointer. So let's have a look at how this memory works, right? So every block of memory has this address. The address is an integer. Depending on the architecture of your computer and the operating system running on it, it depends on what this kind of integer is. Now note, I'm saying integer and I'm not saying int. It is not a C int, but it is an integer in that it is a whole number. So I didn't put this in programming font, and I didn't put in bold or anything, and I didn't use the keyword, but it is a number. But with those addresses, we can find certain chunks of our memory, and with that we can then see what is there, or what and read things or write things to that memory. So like if I gave you a piece of paper that said 1000 Anzac Parade, and if I said just find 1000 Anzac Parade, I think this is a really bad example because I think Anzac Parade restarts its numbering in different places. But it's like if I gave you an address of Pacific Highway, the 700 students would be scattered in different suburbs because it restarts its numbering in every suburb. I think Anzac Parade might do the same thing. So 1000 Anzac Parade might not actually get everyone to the same place, but you would at least know how to follow an address to get somewhere. The same thing in our computer. If I say this is a memory address, I need to get whatever data is in this memory address, we can ask our computer for that and it will help us get there. So a variable is like a house. A variable is a piece of memory. Hello. Someone's saying hi. Can you see it? Oh, sorry. I'll just put it on my lap. There's your lecturer. Okay, so every variable uses some memory, which means it is somewhere in memory, which means it has a location. If it has a location in memory, that means it has an address. So that means it has an address and we can find it. It's the same thing of we're never going to build a house or an apartment without giving it a number and a street and knowing where it is. So what we're going to get is this concept where there's a house that stores information. So in reality, there's a house that stores people and things, but in memory, it's just information. It's a number of bits that have information about whatever variable we're trying to store there. It's nearly always a variable. However, we do store code in memory as well, but we're not going to look at accessing our code via this system. We're going to look at accessing variables by this system. So all of our variables have a memory address and some information at that address. So usually 64-bit system, 64-bit integer storing memory addresses. If we're storing bytes of memory, I'm not sure if we only store a byte at a time. I think it's usually bigger than a byte. But I think you will find out this for certain because different operating systems are going to do it in different ways. So if you continue on in computing and end up in operating systems, which is a reasonably popular subject because it's one of the most important things. Computers don't really run without them, so we do want a lot of students to learn this. You will learn how this works, how we address memory and stuff like that. In C, here we're only going to look at how much we're going to use this for our programming. Later on, you'll look at actual memory architectures and stuff like that. So, the pointer. The pointer is a new variable type. The pointer is a variable that holds a memory address. So, these memory addresses that I've been talking about are just numbers that tell us where in memory something else is. The pointer is a variable that is made specifically to hold the memory address of another variable. So it says, there's this other variable, I know where it is. So instead of saying this is the other variable, and if we look at the other variable we get to see its value and stuff, we're saying we don't really need that other variable right now, but what we have is something that tells us where it is. So pirate treasure map, address of a house, that kind of thing. So we're talking about objects themselves that don't contain any other information other than another object. So they're just something that refers to something else. So I think that's what I'm talking about here. And these points, the pointer is the address. They're always created, well, they're not always created with a particular variable in mind, but they're always created with a purpose to give us access to a variable. So in C, a pointer is not just declared as this number that is a memory address. It is also aimed at a particular variable type, so that when we make a pointer that is for a particular thing. So if I make a pointer that's an integer pointer, then it's expecting the house it reaches to be 32 bits worth of integer. If I make a double pointer, then it's expecting the house that it reaches to be a bigger house and contain 64 bits of data. These houses are not always like, there aren't really different size houses in our memory. Our memory is all made up of bytes, 8-bit chunks. But when our pointer goes to something and looks at it, then it's going to want to know how much of that thing it should read at one time and in what format. Because an integer format and a double format are actually different. And when I say format, I mean the way that the bits represent the number. So you can have all these bits that are ones and zeros, along 64 of them, and that might be a certain representation if it's a double. If it's an integer, it might only use the first 32 bits of that, and that might be a certain representation of a number as well. The way that our numbers and our other variables are encoded as ones and zeros changes depending on the format of the changes depending on the type of the variable. So if we've got that situation, then we want to make sure that if we're going to follow a memory address somewhere, we want to know what type it was looking at when it was getting there. Otherwise we'll just read something out of this house and it'll just be garbled because it's not in the format we expected it to be. So when we're making pointers, the key character that we're using for the pointers is this star, this asterisk. Shift 8 on my standard keyboard here. Oh, it's also on the number pad as well. The star reminds me a lot of the brackets in the arrays. So this is now the symbol that says that a pointer is being used in some way or another. We use the star to declare the pointer. That's what we use when we create a pointer to something. So the type of the pointer is going to be, say, int double. Later on we're going to add other things to this. The type of the pointer is the type of variable that it's pointing at. The star says I'm a pointer. So the star says I am not a variable of this type. I am an address of a variable of this type. Well, I contain an address of a variable of this type. I'm a reference to a variable of this type. And so that's how you say I'm going to be aimed at a particular type of variable. I can then aim it at a particular variable. And this is where we start to use the AND. So this AND, or ampersand, depending on how you want to call it, is a character that we can use with a variable that is like saying, given a variable that exists, if I put an AND in front of it, it's going to tell me the address of that variable. So it's going to tell me where that variable exists. So this is me like going to Google Maps and typing in UNSW, and then I can find an address from that, in a sense, right? So I can find an address by typing in the name of something, and this is the same. I can type in the name and I press the AND here. Well, I put the AND here in my code, and this says I don't want the variable itself, I want you to tell me its location. And I've made a new pointer here because the star says there's a pointer, and the pointer wants to store a location, and so I'm storing the location that I get by putting the AND here. So these symbols are things you're going to get some practice with before you fully understand them. But the AND gets the address, The star is the pointer stores the address. So this is me saying, I've made an integer I, it's equal to 100, just a random integer, not sure what it's used for. This is just a code snippet. I want a pointer to that integer. So for some reason, I would like to reference this integer that I'm going to use in the future. So to do that, I create a pointer that is aimed at an integer. So this is saying it can access an integer type. And I've called it IP. It's just like integer pointer, but I mean, I could have had a longer name for this, but since I'm not using it for anything, I don't really know what I was going to name it there. And if I'm going to initialize this variable, so a pointer is a variable, right? It's a variable that stores a number, and the type it has is what type of data it's looking at the end of that number. So the number is the address. So if I want to store the address here, I need to find the address of an integer, and I do that using the AND. Now, you've seen the AND before in scanf. You may now have a decent idea about how that AND works in scanf, because scanf says, take in what the user is typing in the terminal and put it into this variable. And it's like, how do we put something into a variable? Well, I know a reasonable way we can put something into a variable. We can say, where is that variable in memory? And you go, oh, if I know where that variable in memory is, I know where its ones and zeros are, and I can go and overwrite them. So it's an interesting way of looking at it, that scanf is actually taking as its input a pointer to a variable, and we're giving it the address of a variable by using the AND so that it can access it and make changes to it. So this is why I didn't want to tell you about I didn't want to tell you what the AND in scanf meant until I told you all this theory of the computer and like how memory works, how index addressing works in arrays, and now we get to the point where we can use pointers. So it all has to build up before we can talk about the idea that we can reference variables. So different pointers, different types of variables require different pointers. So this pointer here, an integer pointer, says I'm going to point at 32 bits of memory. When I read those 32 bits of memory, I'm going to expect to see a whole number in those 32 bits of memory. This double pointer here, this one is going to look for 64 bits of memory. So it's going to go, okay, you gave me this address, and then I'm going to read 64 bits of that. And then I'm going to say those 64 bits should end up as a floating point number. So there's going to be information in those 64 bits about where the decimal point is as well as the actual digits themselves. So I'm going to be able to look at that, and I'm going to be able to say, yeah, okay, when I look at this pointer, I'm looking for 64 bits in that format. When I look at this pointer, I'm looking for 32 bits in the integer format. So the pointers aren't just memory addresses on their own. They're memory addresses with some context, some information that says, this is what I expect to find at that memory location once I get there. So when we make pointers, we will often be initializing them when we create them. Sometimes we will be creating a pointer without initializing it. In general, whenever we create variables, if we don't initialize them, we are, I don't know, what's a good way to put this? It's like we've got a path that we're going to walk on again. So the variable's a path we're going to use multiple times, and we're just digging a hole in it and maybe sharpening some bamboo and sticking it in the bottom. So what you're doing if you don't initialize variables is potentially putting a trap there for yourself. If you're really sure of yourself, yes, you can not initialize a variable because you know that you're just about to or something, but it can be super dangerous otherwise. So what we have with pointers is we have a way of saying this pointer is not aimed at anything, but it's not just this pointer, I haven't initialized it, so it has a random value, or if we're lucky, it will always have the same value of like an uninitialized value. But if we want to be sure of this and say this pointer is specifically not pointing at anything right now, we use null. This is one of those few times that I actually bothered to put syntax highlighting in my slides. But capital Null, what do you know from this? You know that if something is all capitals, it's most likely to be a hash define somewhere else. So hash defined null is somewhere else in the code. It's in most of the standard libraries. Standard IO has it. The standard library definitely has it because standard library has all the memory stuff. And the hash defined null just says to us, this pointer is specifically not aimed at anything. So this is a pointer that we might use in the future to aim at something, or this is a pointer that used to be aiming at something, but now we're saying it is not aiming at anything. And your computer will know to deal with that, so that if you try to use a pointer that's not aimed at anything, your program will probably stop at that point and say, hey, you tried to follow an address that is a non-address. So it's nearly like I've got a like you go to the post office and it says the address is like street number and like the postcode and all that kind of information, but you haven't filled it out. It means you can't deliver that to anywhere, so there's no address. If you filled garbled data there, so a random number from not initializing your variable properly, it still might try to send it there. You know, it still might try to go to that location. So null is very safe, because null says no, there is definitely no location that this memory address is referencing. So there's no location for this pointer. So that's why usually if we're not sure what something's going to point at when we make it, then we point it at null first. That's nice and safe, and then we can change it from pointing at null to pointing at a particular variable later. Okay, let's start thinking about how we even use pointers. So the most common thing that we're going to want to do with a pointer is, once we've got a pointer aimed at a variable, we might want to see the variable that the pointer is pointing at. Right, so let me just I find that a lot of the times visuals work nearly better than explanations for things. Okay, so here's my, I'm going to call this I, and it's my integer, and it's somewhere in memory. So let's just say this whole space is memory, and it has the number 12. You know, I'm just making up a number, right? So I is 12, and then I make a pointer. And the way that we usually do this with diagrams is that variables are things and pointers are arrows to things. Having said that, even though the pointer is an arrow to something, the pointer itself takes up a chunk of memory somewhere else. So let's say this chunk of memory starts at the location. I'm going to do this in the format that C is going to do this. I'm just going to make something up. OX756. OX is actually a different numbering system called hexadecimal. Hexadecimal has 16 digits in it, which means it's actually really good when you're working with bytes, and bytes have 8 bits in them. Hexadecimal has 16 different values. They're both divisible by 2, and so it goes in this thing where it's really efficient for computers because everything is in a certain number of bits. Rather than our 10-base number system, which doesn't divide happily into bits in an easy way. It's why when you look at computers, you've always got like, why is RAM always in 8 gig, 16 gig, 32 gig, 64 gig? It goes in this doubling thing, because that's easier for it to address. And then why are these certain numbers always turning up, like 1024, 256? Yes, chicken, see? It's like that kind of thing. So she's explaining. So this is my pointer here. So my pointer here is IP. The value that is stored in my pointer is 0x756, which is the memory location that this integer is in. It's actually nearly like it's not stored in it here, but this thing knows it's an integer pointer. So this pointer says, let me just change this so you can see where I'm pointing. This says I point at an integer, and the integer is at 0x756. So it goes to 756, and we can say, okay, there's a 12 there. There's different ways we can use a pointer. So we could use a pointer by changing this, which is changing the value of the pointer itself. And if I change this value, let's just say, I've got another one down here called J, and it started at the memory location 0x883. I don't know, 888. I'm just making stuff up now. Right. I don't even know if these are valid memory addresses, by the way. So, well, I'm just trying to show an example. So, if I change this number, and I change this number to 888, for example, oops, 888, then this pointer would now be pointing at this variable, not at that variable. I can also, and this is the kind of important thing, so let's say this one has 99 in it. The other thing that I can do, maybe I don't want to change the value of the pointer itself, but I want to go to the variable here, and I say I want to play around with the value of this variable that the pointer is aimed at. I should, if I have the address of something, be able to access it. So there's two ways to do this. There's the pointer itself. So if I look at the pointer itself, I'm going to look at the value of the pointer. The value of the pointer is going to give me a memory address. Or I can, in a similar but not the same, but similar way as an array, I use the symbol for that variable type again, and it's different from here. So here, when I use the symbol, the star, for the variable type, this gives me the creation of a pointer. Here, when I use the star on it after it's been created, what I am doing is I'm asking it to access the variable that it's aimed at and tell me what the value of that variable is. So, oops, I'll tab here. If I say what is IP, it's going to give me this value. If I say what is star IP, the star is going to say follow this to the variable that it's aimed at. Now, just make sure just make sure my face isn't covering up there. Yeah. Now read this value. So there's two ways we can use a pointer. We can use the pointer as the fact that it is a number itself. This is usually for us to store a memory address. And we did that a second ago where I changed the memory address from this variable to this variable. But then we have another way, which is like follow the pointer to its destination and then read what's there. So that's like me saying, I've been given an address, and someone says, well, what's that address? And I say, well, it's 888. And they say, well, what's at that address? Well, just give me a sec. I have to go to that address first. So I go to 888 Anzac Parade somewhere. I don't know. It's not always Anzac Parade, right? I'm just talking about it like in that way so you can sort of understand it. I apologize for everyone who hasn't actually gotten to UNSW. I know that we have a lot of students who have yet to even see UNSW who are in the course. And I'm really sorry about that. That's a really sad thing, because it can be a lot of fun here. But Anzac Parade is the street, the big road that UNSW is on. So what I'm saying is, like, it's just an address on a street. So if I say, what is the address I'm holding? I can see this. But if I say, what is the value in the address once I go to that address, I would follow this pointer to this other place in memory, and then I would read the number that I would find there. That is what's going to happen here when I put the star on the pointer. So putting the star on the pointer says, go to the variable. I'm not interested in the pointer anymore. I'm interested in the variable that's the other end of the pointer. Go there and read that. So this %p is saying I want a pointer address, so I want to read the pointer as if it's a pointer. This %d says I'm going to read an integer, and I know that the pointer is aimed at an integer, so if I follow it to its end and I say look at that integer, it should give me the integer value. I've got some demos of this actually. Let me just see how my timing is going at the moment. COMP1511. We don't have a lecture 8 yet. There's my lecture 8. I'm just going to go to the course website because I have some pointer demo code there. Ooh, is this a pointer demo code? No, no, this is my upload from previously. Pointer demo here. Alright, we're going to download that into lecture 8. Check that it's there. Yes. So this is the code that's available to you. I think I made it I made it 2 terms ago, I think. It would have been, yeah. So mid last year. So here is some code that says, okay, first of all, here's a pointer to an integer, that's 100. And I've got a printf there which says, this will tell us what the address of the integer I is, and then will also tell us the value of the integer. I'm just going to comment out some of this other stuff because I'm going to talk about this stuff later when we talk about functions and things. So I'm going to need to end my main function early here. So this will show you what's going on with those pointers. We'll just call it pointers. Running this, I get this is the address of I, which has the value of 100. So this is a memory address. It's a little bit confusing because it's not really a super human readable number. I mean, it's really not a human readable number, but this, I'm going to rely on the fact that my computer knows where my variable is, and this is the address of my variable. So this is what I get when I take a pointer and I say, what is the value of the pointer? The value of the pointer is the address that's written on my little bit of paper that I'm going to use to get somewhere. Then if I use the star on something, it's saying, okay, take that address, go to that address, and then read what you find when you get there. So this is like me walking to that certain place here on the street, looking in the house and saying, this is the data that's inside that house when I get there, when I'm looking for 32 bits from that location, right? So the star says go somewhere. The pointer itself will give us the value of the address that we were going to use. Okay, that's a little demo. There's more demos as well. So I want to talk a little bit as well. I think Dean's answering all the questions there. Tiara's correct there. Tiara said IP gives the address and star IP gives the value at that location. Yes. Oh, Tiara's asking, why wouldn't you just look up the value without the star and store it? Why do we need the star? So there's two different things. That's just to differentiate the two things that we can do with a pointer. Because one of the things we can do with a pointer is change the value of the pointer, which is the idea that I could change which integer that I was pointing at. In this example, changing the value of the pointer is treating it like a number, and I can change it between these numbers. I could change it to somewhere else as well, but I mean, I'd probably want there to actually be one of my integers there for the pointer to mean something to me. So there's one of the functions of the, well, I shouldn't say functions, one of the things that a pointer can do is it can change where it's aiming. The other thing that it can do is you can follow it to where it's going and then change the value that's there. So these two different things are separate, different capabilities, and so one of them has the star and the other one doesn't. Just a matter of practice getting it. But so sometimes we want to move where a pointer aims, and other times we want to change the value we see at the other end of it. So we have to decide between those. Okay. Let's look at functions and pointers. So if we want to, we can give a function a pointer as its input. We can also give pointers as outputs to functions as well, so with the function type can be that. I should remind you though, and this is something that I've talked about before when we were talking about functions, all function inputs are what we call passed in by value. So you don't get the variable itself, you only get the value of the variable, and then the function makes its own variable when it starts running. So it makes its own set of variables using the values that you passed in, which means usually when we run a function and we give it variables, it does not have access to those original variables. So it can't change the values of the original variables, but it can take the values of those variables and use them in certain ways. Interesting thing with a pointer though is if I have a copy of an address, so if I have two copies of the same address, I can still find the same variable. So I can do something like this, where I have this pointer here, and I make another pointer over here. I'm taking very, very artistic license for where things might be in memory. Usually things are right next to each other, but you never know for sure. So another pointer, I'm just going to call it IP2. And it's also an integer pointer. And I could copy this pointer if I want to. So 0x888. These two pointers are different. They're different variables. They happen to have the same value. But the interesting thing about pointers having the same value is they're both looking at the same address. Which means if I do a star on this pointer, I get a 99. Hang on, I'm going to change my cursor so you can see. And if I do a star on this pointer, I also get 99. And not just 99, they're accessing the same memory location because they're both looking at the same memory location. So I can have a copy of a pointer and it'll still go back to the same place. Right, let me show you this with my pre-made nicer, neater diagrams. So my main function has a variable, and then I call another function. So while I'm running my main, I call another function. So let's say this is a printf even, or something, or another function that I've written, and I put this variable into that function. What happens when I put this variable into that function is this function does not have access to this variable. This variable is owned by the main. This function is in its own space, working on its own things. But I tell it what this variable had as a value when it starts running, and it makes a copy of that variable. So any changes it makes to the variable don't affect the original variable. It just has a copy of it. Interesting thing about pointers is the pointer also has a copy of this pointer. So if I give this pointer to the function, so the input of this function was a pointer, and I had a pointer to that variable, these two are copies of each other, which means any changes I make to this pointer do not change the original pointer. So the pointer being a variable, any changes I make in my function don't change this. However, if I follow this pointer to where it was aimed at, I get that variable that I'm using. And because this pointer here is the same value as this one, if I follow it, I get access to this variable. So now for the first time, I can give a pointer to a variable to a function. I now have access to that variable in the main. So I can go back to something that is stored in the main function, and I can make changes to it because I know where its memory address is. I know where it lives. So I can use the address someone gave me for where something is in the main to now affect things in the main. So now I can give power, in a sense, to my functions to be able to change the stuff in my main. And this gives us a whole lot of extra capabilities. So suddenly, the things that we've created in our main can be our kind of important copies of everything. And we can say, this function is allowed access to some of these by pointers, and it's allowed to change them if it needs to. Whereas previously, it would be like, you can't change any of these variables. The most that you could ever do is output one variable as a function, and then this would come back and then we'd use it. But now we can have pointers to variables so we can change things in our code. So, interesting things about how this works. This we should know already. If I have a function that is void, so a void function, someone's getting hungry, gives no information back. So it does not transform into anything in our code after it finishes running. It has no return value. So no information goes back to the program when it runs. Usually void functions we use to do stuff like print stuff out to the screen and stuff like that. So it can have the side effect of printing text, which we call output. but that's output to a human, not output to the rest of the program. It's like different things, right? There's program output and terminal or console output. So this function here, we kind of know that this doesn't do anything because it takes in an integer and then it adds 1 to that integer. So this integer was not the integer that was in the function, in our main function or whatever called this. This integer is something that is created by increment int, and then it'll add 1 to it, and then it'll just finish and nothing happens. However, if we get given a pointer rather than an integer itself, I will get given the address of a variable somewhere. So if I get the address of a variable somewhere, then I can affect that variable. So I can go to that variable and make changes. So I use the star n to say, go to that variable, and then I say the star n again, and I say, read what's in that variable, add 1 to it, and assign it to that variable. What this will do, this will actually take the variable that was given to us, we were given the address of it, and it will go to that address and make changes. So now, without having any information going back to the program, I'm actually making changes to things that are in the program. Yeah, Priya saying, can you use a variable to access, can you use a pointer to access a variable in another function, not the main? So long as it currently exists, you can. Remember, what goes on inside the curly brackets stays inside the curly brackets. So a function will start to exist when it starts running, and it will no longer exist when it finishes running. So if I have my main, and my main calls a function, that function creates a variable, and then it calls another function, then that function might be able to have access to the stuff that's in this function. But if the function is not running at the time, then its variables don't exist. So it's only certain things that you can access. So it has to be things that are currently in memory for you to be able to access them via a pointer. So if you have another function that's not currently running, so if you look at your step-by-step, your line-by-line, you'll know which functions are running at a time, because you'll call one function, you'll have jumped into that function. If you call another function inside that, then it can look at all of the things that are currently in existence. But if that function has already finished, then you won't have any variables left because it will have cleaned them all up. Things like that. Interesting that this piece of code here, to swap the values of two integers, is actually impossible without pointers. Because if we could only return one value, then swapping two numbers, there was no way that we could retain both of their values, and there's no way we could change the values that we were given, because we're only given values, we're not given access to integer variables when the function runs. However, if we have pointers, it's quite easy for us to swap two values. So I have a temporary one here, so I wonder if I should... Let's just make a new one. So I have, what did I call them? N and M. So there's N and M, and my function, let's say my function has its own piece of memory here that it's using. It gets given a pointer to this one and a pointer to this one. Let's just draw little boxes for them. And it makes its own little variable here called temp as a temporary number there. So let's give these some values so it's easier to work with it. So this is 1, this is 8, and this is, oh no, that doesn't have a value yet. So what this code is actually doing is it's saying, take the temporary, make it whatever was in N. So whatever is N was 1, so the temporary becomes 1. Then make N equal to whatever was in M. So it reads what was in M, which is 8, and it writes it into N. This is the stuff that I can affect with my function, but these pointers are giving me access to this stuff that's outside of the function's memory. So I'm taking the 8 and writing it over the 1. there. And then it's saying take the M and make the M equal to what was in temp. So temp was storing a 1, and it's saying overwrite M with 1. Now my function finishes. My temporary variable, because it was inside the function, just disappears. It gets destroyed by the closing brackets. But now the two variables that existed somewhere else in the program have had their values swapped. You can't do that with a variable if you don't, with a function if you don't have pointers. So interesting little things like that. Pointers and arrays. Here's the subtlety that I wasn't going to talk about when we first talked about arrays. When you pass an array into a function, the variable that is the array. So if I use this array numbers just like this without the square brackets is going to give me the value of one of the elements of the array. But if I give the array without the square brackets, I'm giving you the whole array. And the interesting thing about giving someone the whole array is the array variable, as in numbers here, is actually storing the memory address of the start of the array. And that's an interesting thing, because if it is storing the memory address of the start of the array and I put it into a function, I'm going to get access to that whole array. So it's nearly like if I give an array to a function, it's not precisely the same, but I'm very, very close to giving the function the memory address of my array. So our functions, anytime I have a function that receives an array, it can make changes to the array itself. So we do have to be a little bit careful with that, but this is where we start to realize that arrays and pointers, when they're function inputs, are actually usually interchangeable. So you can give an array as the input to something, and it's the same as giving a pointer to the first element. This is interesting here, where if I print out and format it as a pointer, the address of the first element of the array, or I print out as a pointer the array itself, these will come out the same, because the memory address of the first element of the array is also the memory address of the start of the array, because the first element is at the start of the array. And so these two will actually print out exactly the same number. I think that's in my demo code as well. Yuji's asking, why do we use AND here inside printf? Because I'm trying to find out the address of this variable. So I'm trying to find out where this variable is in memory, then I'm using the AND here. So what I'm showing is the AND is saying the address of this variable and this variable are the same thing because of the way that arrays are built. Okay. Fun bit. Pointers, hang on, covering up the meme. Pointers aimed at other pointers. Pointers are variables. You may have seen this before. I've run out of memes that are about things referencing themselves. So I had to use the Yo Dog meme for I think it was looping inside loops. I had to use Inception for putting arrays inside arrays. And then I found another one where I could have something aimed at itself to be pointers at other pointers here. So I had to use the Spider-Man meme. So like this is the hardest. This is like this is my alpha level meme game. To teach you so many different ways that things can reference themselves with the right meme every time. So a pointer is a variable. Chicken, I know this is a very important point, Chicken. So she's trying to drive this home because it's important. If pointers can point in variables, but pointers are variables, that means pointers can point at pointers. There are uses for pointers to pointers. They are reasonably complex, and they are at a level that we're not really going to go into in COMP1511 because I think we need to learn the basics of how these things work before we start building on the subtleties. So unlike arrays, whereas like we can put arrays inside arrays, and I think you should be able to learn that immediately on learning arrays. Pointers to pointers are a bit more of a make your brain twists a bit, and then it doesn't work that well. So we're not going to use pointers aimed at pointers in 1511. But bear in mind that they exist, and they will come and get you at some point. Right. Um. Oh, a pointer to itself. I guess you could. I don't know about you, Dean, but I can't think. Sorry, someone asked a question. What about a pointer to itself? I'm not sure where I would use that. If I wanted the memory location of a variable, it's usually because I want that variable for a particular reason. Anyway, oops. I changed this for a slide for something else. But it's time for a break. And I thought, because I haven't said that much about the assignment yet, I would at least put something up here about the assignment. So our first assignment is called Freefall. It is a simulation of a certain type of vertical shooter classic arcade game like Space Invaders. Space Invaders was, I think, the first of the vertical shooters, and then a bunch of them came afterwards. Like Galaga is a like standout one, because I think it was the one that a couple of years after Space Invader was like the second game in the genre that sort of knocked Space Invaders off its perch. We have a way to play the game, and so I thought I'd just leave this with you. I think your tutors are talking about it a lot this week anyway, and I think I also put a message out that the assignment spec was available, so all that kind of stuff. Have a look at it if you want. Tomorrow night, or tomorrow afternoon, we are going to be doing a live stream on that as well. But for the moment, we're going to go on break, which means this is the point that everyone's been waiting for. I will get Chicken's food, bring it in, and set up the camera so that you can watch Chicken eating. But I'll be right back. Just setting up the camera. Ah! There we go. Yes, yes, it's food time. Okay, is that in the right place? There we go. I'll get out of the light. Okay. Going to move you back up here. I feel like I should probably turn the camera off before I move it around, but you know. Alright. I was wondering if I have any like boxes of deliveries down there that I'm accidentally showing you my address. Let's be careful not to say it. It's probably like in my room somewhere. Okay! Let us continue. Oh, Dean. Dean's confusing Terry. Just to confuse you, functions are pointers. we'll get to that. Actually, we're not even going to get to that in 1511. Function pointers are a next level thing. But when you consider, right, I told you that everything is in code. Which means that the instructions that we run, the functions that we run are also in code. Everything's in code. Everything's in memory. The functions are in memory, which means when we hit a function call, the function's actually going to tell us where that bit of memory is that we run. And so it's going to say, here's some information about inputs, but here is where you jump to run that code. And it's like, oh, okay, so we jump to another piece of memory, and then we start running code there, and then we jump back to where we were. So when you think about it, a function is just telling you where to go in memory for the instructions to continue running, as opposed to a pointer, which is saying where do we go in memory to read the memory as if it is a variable, that kind of thing. So, yes, Terry, you could have pointers to pointers to pointers to pointers. Later on, I will show an example of that. You can do it. There's not always a great reason for it, and there's a good reason to say that doing that is going to confuse the hell out of people, so not always a good thing to do. Kyle has noticed a string is just an array of characters. Yes, but since we haven't said anything about characters or strings, all I'm going to say is yes. I'm going to explain that all later. We're going to get to that. There's a lot that we want to learn about the fundamentals of how to work programs before we need to add in different variable types. You know, I could even have just said neither ints nor doubles and just said ints, and we'd still be learning so much about programming even with ints. I mean, most of my examples are just integers anyway, but we use doubles when we want more precision or other things. But we could do a lot with only one variable type and still be learning so much about the structural idea of how programming works, and how we're making the back end of a game in assignment 1 just using integers, you know, so we can still do cool stuff like that. All right, let us make a program. I'm just gonna, so you can read it, using functions and pointers. I call this one the jumbler. What it does is it takes numbers as inputs and then it messes them around, changing the order of them, and then prints it back out. So it's a pretty simple thing. It's not even going to be doing that much in terms of actually randomizing. It's not really randomizing it. It's just taking in numbers, swapping a bunch of them, and printing out. So I'm going to use that swap that we're talking about. We're going to use our functions here to separate our code into different things, and we're going to use pointers to access memory. So, put my face back up in the corner. How do we split up our functionality? So we can look at the different things I've said we're going to do. We can read inputs and then put them into an array or something like that. And so that can be part of our functionality. We can have a function that swaps two numbers, and then we can have a function that goes through our array swapping several different pairs of numbers. So we can write a function that does a simple thing, and then we can write another function that uses that simple thing multiple times in different ways. And so that's what this is going to be. We're actually going to do a function inside a function, because it's good for you to at least see that once. And then we have a function that prints out all the numbers at the end. This should be the easiest one, because I think by now we probably know how to do a simple loop through an array to print out numbers. So let us have a look at the code itself. I should actually start the code. So I'm going to go across to our VLab here, and we're going to make a new program called the jumbler. Autocomplete changed my word entirely. Jumbler, a demo program showing the use of pointers and functions made by, oops, type in every letter. What are we? Still in June 2020, the longest year in human history. Okay. We're going to need our standard input output. I'm just assuming that we're going to need that. I haven't checked. But there was something in our thing that was saying going to print out stuff. I know also that if we're going to play around with memory and pointers, I wonder if we're going to need our standard library. I'm not sure, actually. You know what? What I'm going to do is I'm going to do this in a sort of minimalist way. I'm only going to hash include things if I definitely know I'm going to need them. Otherwise, I'm just adding code to something unnecessarily. So what I'm going to do is I'm going to say, all right, for now, I know that at some point I'm printing stuff out. So I'm going to have standard input output. So I have a function. What was I calling it? Read inputs. And read inputs was going to take an array, an integer array. What are we calling it? Nums, because it's an array of numbers. Yep. Max input size. I should just do cat puns in everything that I'm doing. I'm not going to do that. There's comedy, and then there's bad code style. And we're not going to sacrifice the bad code style just for the sake of comedy. So I've already said max input size, so I know that I'm going to have some kind of limit on my input, and I haven't decided what that is yet. So I know that if I'm going to go for a constant like that, I'm going to actually want to define it. So max input size, let's say, for example, we're just going to take this easy and say we're not going to have a massive number of integers as input, but we want enough so that most of the inputs we're going to use are going to be okay. So if I say 100, I don't really want to do this demo in front of you and ever be typing in more than 100 numbers. So this is actually quite high compared to what I'm going to use. I'm probably going to use like 3 or 4 numbers at a time. But still, I think it's fair enough to have this in case something gets bigger than a certain point. Some people get really full on about these things and go, you know what, I'm going to have enough space for a massive thing just in case this thing's going to need it. I'm not going to go that far overboard for the moment. I'll just say max is 100. Okay. So if I'm going to make this function, I have declared the function there, and then I will define the function here where the actual body of the code is, and I will talk about what it does. Reads input integers from standard input and inserts them in order into the array nums. Let me just check, because I can't remember what I was doing with the output. Right. So you can see from this code here that I've written previously that this thing's first going to check how many numbers someone wants to input. So the first number that we read is not going to be going into the array. It's going to be figuring out how many numbers it's going to read, and then it's going to read that many numbers in, and it's going to return the number of inputs that it was supposed to have read in. I wonder if we don't actually want to return the number of numbers that it was supposed to read in, but we actually want to return the number of numbers it did read in, because that might actually be a better way of doing it. Okay, so this comment's not entirely correct. I'm going to say reads a number from standard input, then what is delete? There you go. Then reads that many input integers from standard input and inserts them in order into the array nums. I'm just making my stuff pretty. Okay. So the first thing that we're going to do is read how many. I don't like that int 0 there. I'm going to put the int 0 where the loop starts. One of the things that we often like to do with variables is we create the variable as late as we need it. So we only create the variables as we're about to use them. There, I think I started, when I was writing the slide, I started thinking about that loop before thinking about the input count. Okay, so int input count. I'm going to set it to 0 before I do my scanf or anything. So this means that if something screws up and I don't read anything into the input count, at least I'm just not going to read any inputs. So it'll be simple. So printf, oops, how many numbers, and I'll leave a space there, and then the person can type in how many numbers. I will scanf those numbers into input count. So this is me giving the address of input count. So I'm giving a memory location. Scanf is going to write the number it reads into that memory location, which means I'm giving, as an address of input count, I'm giving basically a pointer to input count to the scanf so that it has access to this piece of memory and can change that number that's in there. Alright, so after I've done that, I'm going to set up my loop iterator. And I'm just going to make sure that all of this is there before I start doing anything in my while loop. And I'm going to say, I'm going to keep looping until I ends up equal to input count, but I don't want to go off the end of this array. So I'm going to have another thing here that says I has to be less than input count, but I also, see, sometimes when I talk about it in English, I can pick out the keywords that are going to tell me which code things to use. So if I want it to be less than the input count, and I also want it to be less than the maximum input size, then I'm looking at an AND. So I has to remain less than both of these numbers. So if it gets above either of these numbers, then we know it has to stop. So if someone says, I want to enter 300 numbers, and I've said you can only enter 100, then like this is too much, right? So here it's going to say I will stop at whichever of these is the smallest, basically. Now each time it loops, it is going to scanf a number, and it's going to put it in a certain location inside this array numbers. So scanf always wants the address of something, so I'm going to put the AND there for the address, and it's going to be in the array, and I'm using I to loop through the array, so I is where I want it. So important, have processed I inputs. Sometimes I like to put these here because they help me to know every time this is looping, I can think about what value is I going to be, what does that mean? So if I've gone through once, and then my second loop through I is equal to 1, and I know that at this point I've processed one previous input. And then when I get to the end here, I then equals the actual number of inputs scanned. So I might actually go and change what I did from my slides. I notice now I haven't got a comment here for this, which is bad. I'm returning an integer, but I haven't said anything in the comment about what I return. Returns the actual number of ints scanned into the array. Okay, so if I return I there, what read inputs now is going to do is it's going to ask the user how many numbers it wants, the user wants to type in, and then it's going to tell the program how many inputs it actually read, because it's going to add one each time, and then at the end of this I will equal the number of inputs scanned there. So it's either going to be the number that the person gave us or the max input size, assuming that nothing goes wrong in here. I'm not gonna try to deal with what could go wrong there for the moment. Right, so this is our function for read inputs. So what I can do now is I can say int, it doesn't even have to be called nums, I could call it numbers, which is also going to be max input size. So this is my array. I'm going to do the safe thing, and I will nearly always do this with an array where I don't have specific values that I want for it. I will just make them all zeros to begin with, because it's safer to have everything as zeros rather than not setting up an array with any particular values. Okay, so my array is set up. It's full of zeros at the moment, and then I can say int, what is it? Input size? I think input size is a decent name for that. So I'm counting how many things were input, so its input size is equal to the result here of read inputs. So read inputs is going to return to me the number that was in here in the while loop. So I kept increasing every time we added something to the array, every time we scanned something into the array, and then at the end it's going to tell me how many things were in it. So input size is going to be the output of read inputs. Read inputs wanted to know where to put things, so it was looking for an array of integers that's of max input size. I have an array of integers of max input size, so I'm going to put numbers in here. Okay, so this at least will get me to the point where I can take input from the user and I can put it into an array. Lots of questions there. I'm not sure if Dean is still there or not. All people are just talking fast. I'm going to let you talk there, and I will continue the example here. But if you still got questions after the conversation that's happening there, stick around afterwards, and I'll talk afterwards. But I think I want to, like, within the 2 hours, deliver the content that I want people to see. Okay, so input size is equal to read inputs and the numbers. So for the moment, we don't have any way to check whether this works or not. So the next function I might make would be the print output function. Let me see if past Mark thought the same thing. Yes, past Mark thought the same thing. Let's be able to print this out so we can check whether our input is working. So print nums is something that's going to print out everything that's in the array, but it's not going to print out the whole length of the array because I'm only using part of it. So I have this potential big array, but only part of it is the values I actually want. So I'm going to keep track of how much of this array I want to use by saying this is how much of it, the number count is how much I want to use. So let's come back here, and this is a void function because the output that it gives is not a program output. It's not information that the main needs to get back. The output is a different kind of output. It's human output. So the printf is not really considered function output. It's considered a consequence of the function, not the actual function's output. So print nums is going to take in an integer array that is of max input size. And it's also going to take in a number that says how many things it's going to print out. So I don't know what I want to call that. Print quantity? Yes, it sort of makes sense. I'm going to take this function and I'm going to write it down here. So you can sort of see why I'm pushing these down here, because I do want my main to be at the top. here so that I can see what my program's doing kind of on the first page. It's not always going to be on the first page, but I try to keep that at the beginning so I can find it. And then the complicated stuff ends up down here. So this is prints out the first print quantity integers from the array nums. Okay, so we're going to go through this array, print it out until we reach this number, or maybe we reach max input size, because I don't know if there could be a mistake in print quantity and we could go higher than max input size, so we do want to do the same thing where we check for both. So, basic loop here, using I as the number that we're going to go through the array with, and we don't want I to get over the max input size, and we also don't want I to get over the print quantity. So this will make sure that we get that right number. I'm gonna leave these comments in. Have printed I numbers. Whoa, just inside the line width there. Okay, so the actual thing inside the while loop that's doing something is a printf. I might just put a space there. So this is going to do all the numbers along one line. Let me see if I had anything. Yeah, I did the same thing there. Yep. So printf there, and then the actual number we're going to print out each time is part of the array, but it's the I element of the array starting from 0 and going on up until we reach the point where we're not going to print anymore. So this should print them in a row. So if I type these numbers in, I should just get the same numbers back. I don't need a return in this function because it's a void. A void function does not return any information, so it doesn't need the return keyword. Okay, so this function here should now print things out, which means I can do this. Print nums wanted an array, an integer array, and I have an integer array here called numbers. And it also wanted a quantity that it was going to print, and I should have that quantity here in the input size. So if I run this now, it's going to create an array called numbers. It's going to create an integer called input size based on it reading in the numbers, and then it's going to print out the numbers. Note what's going on here with my main. My main is very, very short, and it's nearly entirely English language words. There's numbers that are max input size is read inputs, and print numbers. So we can nearly give this to someone who doesn't know C, and then they can read this. They can be like, okay, you're going to read inputs and then print numbers. I'm not sure what everything else is going on here, but I'm pretty sure you're reading inputs and then printing numbers. And all of this confusing stuff with, like, you know, specific C syntax on how to do looping and stuff like that. They don't need to know about that, but you can actually read this and have a good idea about what's going on. Also, super easy for someone who's working with you to know the flow of the program, because the details are hidden. This is one of the things that functions do really well. Alright, let's save this and do our first test. I'm just going to clear that because I don't need all of that other information. So, DCC of jumbler, and I'm just going to call it jumbler as well. I mean, I very often use the same program name as the C file name just because I have they're the same concept to me. Like, one is the file that runs and the other is the file that contains the instructions that runs, and so they're usually going to be the same. So, running jumbler. First thing it's going to do is ask me how many numbers I'm going to input. Let's keep this easy on ourselves. I'm going to input 4 numbers. 1, 2, 3. Oh, check this out. I can press enter in between this, but it's still waiting to scanf another number. So I could put my 4 in another line, and this will still scan them all in as separate numbers because it sees that they've been separated by spaces. There we go. So we have read in the numbers 1, 2, 3, and 4. We have stored them in the array, and then we've printed them back out. This, I think, people should be a little bit familiar with by now, because a lot of our lab exercises have bits like that where it's like, okay, read in some stuff, do stuff with it, spit it back out. Here is not even doing anything with it. It's just reading in numbers with multiple scanfs and then spitting them out. I did want to kind of show you a little bit of the subtlety of scanf there, that all white space it just ignores. So it can ignore a space, but it can also ignore a new line. But then printing it out, it's going to print out exactly in the format that I said here. It's one space in between each number. I might, to make things easy for myself, and just make things neater, print a new line at the end, so I don't get this kind of thing where my terminal is attached to my last line of input. I like to keep them separated. Dean likes my functionizing. Yeah. Maybell, good question. Do we not comment on the main? What I consider is that this is the comment for the main. You can definitely put comments inside the main. If there's complicated stuff here, you can. For the moment, with my 3 lines of code with a whole bunch of English language stuff in there, I don't think I need comments in my main. Like, I think they may just confuse people. But if I want to tell people what the whole program does, I will usually do it in the title here. However, I didn't really show, like, before I upload this later, I will probably change these comments to have a bit more information in them. So it's not just a demo program showing the use of pointers and functions. It's a program that takes in a set of integers, swaps some of them, and then outputs the array. That's what I should have said up here, and then it would be more clear about what's happening here. But yeah, I thought that was a good question actually, about like asking where we do or don't put comments. The only reason there's no comments in my main so far is there isn't enough code to confuse someone yet. I mean, there's even not that much comments in these, because especially this one's a simple single loop. However, each of the functions has a really clear idea about what its intention is. Okay, so where we are now is we can read input and we can print output. So if we go back to our list of things, function that I just tried to select stuff in the presentation mode, function that reads the inputs, function that prints out our numbers. So in between, a function that swaps 2 numbers and a function that swaps several numbers. So actually no, I'm going to stay on those slides for a second. No, I have to go back. So we've got reading input and output. Now, using pointers to swap variable values. There was a reason why I showed you this before and showed you how it works. The swap function will take pointers to integers. And the interesting thing is that when we get pointers to integers, we don't even know if they're in arrays or not. We just know they're in memory somewhere. So we can give the addresses of any integers and say swap these two, and we should still be able to do them. So let's write this swap nums function, which will be able to take any 2 variables somewhere and swap them. So it's also a void function in that it doesn't give any information back to the program, because the program doesn't need any information back from this. But now I'm going to take 2 integer pointers. I'm probably going to have to name these, but I don't really have any particular names for them. This is one of those cases where if you use single letter variable names, I would probably be okay with this. Our automated style checker will probably not like it, but I'm gonna see what it thinks about this. I'll run 1511 style on this one when I've written this function. So there's A and B, and I'm going to swap the values that are at the other ends of these pointers. So we know that these are pointers because of the stars, which says this is a pointer to a variable, and I'm going to call that A. This is a pointer to a variable, I'm going to call that B, and I'm going to swap the values I find at the end of those pointers. So copy that, paste that here, and get it ready for implementation. I'm just going to put some enters here so it's close in the middle of the screen, just easier for you to see. And I'm going to say swap the values of the integers that the pointers A and B aim at. I always like to think about pointers as if they're aiming at something, because it helps me to remember that there's something at the other end of the pointer that's the actual object. But the pointer is a thing that can aim. So it's an object and it aims at an object. I use the word object because I can do that in C, because we don't have the concept of objects in C. If we're teaching another language, then object is also a keyword, and I'm not using it as a keyword at this point. Okay, so to swap things, what I'm going to do is I'm going to set up a temporary variable, and it's going to be empty, because it doesn't have a value yet. Oh, actually, it doesn't have to be empty. I could make it equal to the value of one of the pointers. Note, very careful. Same way as arrays. So when I look at this array here, num's max input size, this is saying that this array is this big. When I use it here, it is not saying anything about the size. It's saying this is the index I'm going to use. So the square brackets have a different purpose here than here. And it depends on whether I'm making the variable using the type, or I'm using the variable after it's made. This is exactly the same here. The star has a particular meaning when you're making something, and it has a different meaning when you're using it. So when I make a pointer, the star just says this is a pointer to an integer, and it's called A. When I do this, I'm saying star A. This is not making a pointer this time. This is using the pointer A. This is going to follow A to its destination and then pick up the information that's there. So this is me saying, what number was A pointing at? Store that in the temporary. Then, because I've saved the number from A, I can overwrite the number that's in A with whatever number was in B. And then I take, because now I've saved the value of B in A, I can overwrite B. Oops. B is now equal to what had been in A. So this simple sort of three-part thing is how we swap things, because we can't just swap things in memory. We have to pull something out, replace it, and then put something in, because we can only do certain things at a time. So this is going to be a really, really simple function that's going to swap A's and B's. So I'll save that. Let me just compile that, make sure it compiles. And let me see what 1511 style thinks of jumbler. Style feedback tool, indentation red and green. Error, no ZIDs in header. I didn't put my ZID in the header. This is how you can see that 1511 style is aimed at you, not me, because I made it pretty clear who I was in the header, and I even left an email address so that I can be found. But I don't often put my ZID in things, whereas for you, you should put your ZID in things, because we're going to be assessing you. And when you have 700 people in a course, we have before had 2 people with the same name. So it's like no end of confusion. It's like, hey, this student, and someone else is like, what do you mean? That's my student. It's like, no, that's my student. It's like, oh, there's 2 of them. Admin loves you if you have the same name as someone else, because it gets super confusing. That's why we want ZIDs, just in case. Okay. No ZIDs in header. Alright. It likes my indentation. It actually had no problem with me using A and B here. So I think that the style tool at this point thinks it's sort of okay for me to use some generic variables. If I use too many single letter variables all through my code and they're all just random letters, it would probably say, hey, I think you might have a problem there. Otherwise, it thinks my style is okay for now, which is good. It should be. I shouldn't be writing bad style in lectures unless I'm specifically trying to show you something. Okay, so we can swap the values of the integers. Let's have a quick test of that, at least. This is a super dodgy test, by the way. And we were talking about commenting in main. I'm going to write this. Super dodgy test. Do not leave this in the final code. I'll do this sometimes. Or sometimes I'll even say to do. And you see how that gets highlighted? It means it's easier to find this thing later. So to do means I'm going to want to do something here later, which is to remove this. So I'm just leaving a note for myself there. So what I'm going to do is swap nums. and I'm going to swap the first two elements of the array. This could be super dangerous if I haven't put anything in the array, but maybe it's okay, because even if I haven't put anything in, it's all zeros. But anyway, I'll swap nums, and I need to give it 2 pointers. If I don't want to give it pointers, I can give it memory addresses. So if I give it memory addresses, they start with an AND. This is the address of a variable. And let's say number 0 is one of them. And then the address of numbers 1 is the second one. So I'm going to say swap the first two for me. I think Dean's answering all the questions there. That's cool. I'll talk to you later about questions. I have code that I want to show. Okay, so let's see if this swap numbers here works. Did I save that? Yes. Going to compile this and run it, and it says how many numbers. Let's just put in 3 numbers, and just to make it simple so that we can see what's going on here, I'm going to put 1 2 3 in, and then it gives me back 2 1 3. Cool. This is a good start. I know that my swap function is working. So I'm not only showing you the way that I am making things into functions and stuff. One of the other things I want to show you when I do code for you is how I test things. So every time I write a small section of code, I will test it before I go on to build up more code. The more code you write in between testing, the harder it is to find the problems that you have in your code. So I like to test it every time I do, you know, like I had written like this function, then I stopped to test it. Then I write this function, and I stop to test it. And if I want to be really careful about this, I might want to do this with multiple different tests. But for now, I'm just going to leave it with that test, because I'm reasonably sure about it. I've only got that much. I don't have a super amount of time to go through and really thoroughly test everything. And when we do the second assignment, we're going to actually get you to write tests like this to make sure things work or not. Okay, so I've got my super dodgy test, and I've removed my super dodgy test because it is super dodgy. But the next thing that I was going to do is write a function that uses the swap multiple times to actually jumble things. So we've got the simple swap function, and we have this jumble, which is going to go through and jumble multiple times. We could do jumble in many different ways. I'm just going to do a really simple one. So void jumble, and it's going to take in an array. Looks similar. It's working on the same array that the other functions were working on, so it's taking the same thing as input. Are we taking anything else? Oh yeah, we need the number count. Because if we don't know how many of these things are in there that we're actually using, we're going to end up jumbling stuff that we don't need to, like all the zeros at the end. Just in the back of my head, this was my variable name that I thought of for this, and it like in my rules it makes sense, but when I look at it, it just looks so stupid to me. But I'm going to leave it in because it still makes sense. Num-nums. Int num-nums is the number of numbers. So I have managed to put num-nums in a program. So int number of numbers is the number of the numbers inside there. Look, okay. If we want to just get serious about this and be a proper programmer, we could just say length. But it's not technically the length, because this thing's much bigger than this. It's actually the number of numbers in it that we care about. So I have fully justified using num-nums as a variable. And it's staying. Shady accidentally typed bum-bums. Nom-noms. Someone else typed nom-noms. Yeah, okay. We're going with this. We're going with num-nums. I mean, we did just feed chicken before we started this example, so num-nums have happened in this lecture. Okay. Jumble. Use swap nums repeatedly to change the order of the numbers in nums. So what we're going to do now, this is up to choice, really. Like, there's nothing that specifically says how we're going to do this, because if we're just jumbling something, we just want to mess it up, you know? So we don't have to have a proper technique for what we're doing here. I'm just going to make up a technique for what we do. So first thing I'm going to do is I'm definitely going to loop through the array, and I'm going to loop through the array picking numbers, and I'm going to swap them with other numbers, and hopefully that'll be enough to jumble this thing up. So as you can see, building my structure here for something that's going to loop through the whole array before I even decide what I'm going to do with it. At least my structure is correct. So I is less than max input size. Maybe I'll do this in the same order I was doing the others, max input size. I've kind of reversed the order on some of these. Not a huge difference. So I'll just leave it as it is. It's less than max input size, and I is less than nums. So this means it's going to loop through just the numbers that we've actually input into the array. I'm going to want two variables to swap. So I'm going to make another index called j, which is going to be a different number in the list. And j is going to be equal to I... What did I do last time? I times 2. Okay. I times 2 could give us a problem, because I could then end up creating array indexes that are out of bounds. So I could accidentally, with this j, go off the end of the array, or even into the zeros and lose some of my values. So I want to make sure that I'm not doing that. I did it one way in the slides, but I just thought up another way that might work. I times 2 mod nums. This way I get to use more nums. So what I've done here is I've said that if I'm going to mod it to nums, then the result of this number will always be between 0 and 1 less than nums, which is exactly the possible indexes in the list. So if I do this, then I and j are going to be just two indexes somewhere in the list. Even if they're the same index, if I accidentally put them on the same index, swap nums is still going to be okay with that. It's still going to be able to work with that, I think. Yes. Hopefully it won't lose values, because I think because of the temp, it'll save 1, and then it'll put it back over itself and then put it back. Yeah, so it should be okay even if they're the same. So this, I should comment this because this is weird. Find another index in the array. Does not have a particular reason. It's actually a kind of random other index. I'm getting a little bit loose with my comments here, but it is sort of still explaining what I'm doing there. So there's int j. So I've got I and j. With that, I have two variables that I want to swap. So I'm now going to call swap nums on those two variables. But swap nums takes pointers to those. So if it wants pointers, I must provide it with memory addresses. If I want to give something a memory address, I give it an and then I find the variable itself. So the variable is going to be in the array nums. It's going to be one of the variables in the array nums, so let's take the I. And the other one that's going to swap is a variable in the array nums called j, but I don't want to give it the variable. I want to give it the address of the variable so that it can find it again. So the pointer can be given an address here. And this is going to go through, and it's going to do some random swaps in the numbers. So let's come back up here to my main and say I took my input size I read the inputs, now I'm going to jumble them. So jumble numbers, and the number of nums is input size. There. Again, I want to point out what my main function is. This is my whole program. It's doing all this stuff, but this is my whole program. Make an array, read the inputs, track how many inputs we read, jumble them, and then print them out. I can read this whole program just on function names. And then the code's here. So the read inputs has got this looping, it's got output and all this kind of stuff. The print has looping as well. The swap has pointers, and it has this temporary stuff. Interestingly, this function does not exist in the main. It is not used in the main at all. It is used in another function. So jumble uses swap nums. So this is the first time we've had an example of a function that, while it is available to our main never uses it itself. It calls another function, which is like what we would call a higher level function, that then uses this lower level function multiple times. So this is one of the nice things. Like, I could have put all of this stuff in here, but again, that would make this one quite confusing. And then I'd have to have all this other imports and things like that going on here. So instead, I have this as the simple thing, and I can use it in this. And we do this a lot when we're programming, because if we make functions of simple things, we can test them to make sure they work on their own before we throw it into something like this. And then we could have gotten in a lot of trouble if we had a bunch of pointers floating around in here and we weren't sure what they were doing. So that's why we do this one first, then this one. Alright, let's save this and run this and see how it goes. So wait, save, and then compile, and let's run our jumbler. So let's put in 6 numbers, 1, 2, 3, 4. I just want to show off what scanf can do or what it can ignore. 4, 5, 6, and the numbers have been jumbled in some way. I'm not sure exactly, because I don't know exactly how they would all come out, but the numbers are no longer in the order that I put them in, and we've done that using pointers and functions. And look how pretty my main function is. This is like, yeah, this is what I love main functions to be, because they're super readable like this. I just read this, and then I read this, and I read this, and I know that that's an array, and that's all I need to know. And all the messy stuff that you might lose stuff in is here, but it's all quite clearly commented all through here as well. Okay, sorry, I've gone over time by about 5 minutes, so I'm going to end the official lecture here. So I'll just go onto the break screen for a second so that people scanning through and they're watching it can see. So I'm going to end the official lecture here. What I'm going to do is I'll stick around afterwards, because I'm sure that there's a lot of code here and a lot of stuff in functions and some stuff in pointers and stuff that people are going to want to talk about. So I'll stick around afterwards and answer any questions anyone has. But if you're looking for just the content, that was the content for the lecture. So I'll be right back. Alrighty, I'm back. What are people asking? I think I went a bit fast there because I'm seeing people saying that their brains got fried by that one. So maybe this is one that you want to go back and look at again. Okay, couple of questions here. Catherine asks, if one function uses another function, does it matter what order they're listed in? The order that's important is that if anything wants to use a function, it should be in this list up here, or in this here, which is why we don't open any curly brackets until after these things are written, right? So we don't, the open curly bracket signifies we're going to write code that runs, and this is just declarations of code that has a potential to run, but it doesn't run until down here. So if we say that these things exist, then we can use them because they told us what the inputs and outputs are. So if these declarations tell us what the inputs and outputs are, then we can use them. And when we have the case down here of jumble using swap nums, it might be that it jumps to here, but it doesn't need this. So it doesn't need this to be before this, because even if it wasn't before that, it would still know what swap nums was in terms of what values does it give it, what values it's going to expect back from it. So it's always going to know what it is, regardless of whether these two are before or after each other there. Oh, Shady's already answered that. Shady asks, is this a good encryption method? So there are different encryption methods. What you'd want is for this to change things around to the point where you could reverse it in a way that made sense. I don't think it's a great encryption method because it leaves all of the same numbers that were typed in. I would prefer an encryption method that would change all the numbers to things that weren't necessarily numbers that were typed in, so that if I typed in letters, they would end up numbers or something like that, you know. So things get shuffled around in such a way that it's not just changing the order of the letters. Because if you look at, like, you know, like those puzzles where you get 9 letters and you have to make words out of it, humans are actually pretty good at making words out of that. There's a chance they'll be able to figure out what your word is. And if they figure out what one word is, then they'll be able to reverse engineer the order of the swaps that got it there. So I don't know if I would necessarily use it for encryption. Williams asked, if you typed the same numbers again, would it jumble the same? Yeah, it would. There's nothing random here. I have not taught you random number generators yet. I am at some point going to bring some random number generators into this. So one thing I could do is, yeah, I is equal to 0, I loops through, and instead of j being this, which is a purely deterministic mathematical function, if I said here, create a random number between 0 and num-nums. Wait, num-nums minus 1. Don't want to go out of bounds on our array. Oh, num-nums or max input. Well, the lower of those. I'll just say num-nums for the moment. If I could do this, then yes, it would be different every time. But because I did this instead, it's the same maths. So we're trusting our program to do the same thing again. Shady's talking about seeds. When we do random stuff, we'll talk about how we can seed a pseudo-random number generator, but I'm not going to talk about that today. We could, in terms of a seed here being a number that we added to the I before we doubled it and modded it and stuff, and then that would change things, maybe. Liang was asking me to scroll down to the jumbler. That's good, because I'm here right now. Really, when you think about it, it's a loop. It's a simple loop that swaps two numbers, but this is just this weird thing that just chooses what it's going to swap with. You don't even have to do the same thing as me. If you can write something here that just guarantees a number between 0 and 1 less than the smaller of these two, num-nums or max input size, then you'll have some kind of jumbling, right? So I wanted to make this clear in these comments that it wasn't for a particular reason. It's just a kind of random other index. It's not even random, it's a kind of random. So even this language sounds really kind of, really just like the way I speak, it's sort of, it actually makes really specific sense. Nearly like that's how I speak. I speak in a casual way, but I'm very, very clear about what I'm trying to teach you. I hope. Michael Ling is saying, pretty sure this isn't random, only pseudo-random, and I think that is the case, yes. Jeffrey wants to look at the read inputs function. Let's have a look at the read inputs function. I can even answer other questions while you're looking at this one. So, read inputs says the first thing is it scans in a number saying how many inputs you want. So this is reading and then writing, and then it has an input count. Standard scanf stuff here. Like this is like week 1, right? Oh no, week 2. Maybe. Could have been week 1 even. You're reading it into a variable, and so you're changing that from 0 to something else, and then you're doing a loop using that variable or the maximum as the maximum, and then each time you loop through, you scan in a new number into a new location, because the I++ is going to change the locations in the array. Where were we? That was Jeffrey. Shayek's asking when our next weekly test is. That's a very good question, because it should have been released, but I think I didn't press the button. If it's not out now, it means I didn't press the button. I was actually up last night at 2 or 3 a.m. when it usually gets released automatically, but I think I didn't set this one to be released. Having said that, the current one is not due until 8 p.m. So I may release the next one at 8 p.m. so you can finish one before you start the next. I'll have a look at it and check if it's not out. Unless someone can tell me it's out already, but I have a feeling if you're asking that, it means it's not out. So I just need to press the button and release it. But that's okay, because I don't always want to overlap the releases, because it's like I don't want to pile double work on you. But then sometimes people want stuff early no matter what, so I can understand. I will try to get it out like pretty much after I log off now. I'll do all the normal things. I gotta like upload the stream and all this kind of stuff, but I will, and the code, but I'll try to make sure that weekly test definitely comes out sometime around when the previous one is due, which is in a couple of hours. Terry's talking about the assignment being stage 1 and stage 2 is around 75%. Yeah, it kind of makes sense. There's 4 stages for the assignment, and completing stages gets you, like, so it's not like, imagine completing stage 1 and only getting 25% on the assignment. So that would be implying that we're asking you to do stuff that's not really worth much. But stage 1 is the base competency level for where we're at the moment. It's the ability to loop through an array. So if you can loop through arrays, and they're non-trivial loops, there's 2 different loops you have to do, and they're not super easy, that shows that you understand how to use arrays, and so we'll give a passing mark for that kind of thing. And then it's kind of like the rest is a scale for the rest of the marks on how interesting, tricky stuff you can pull off with arrays and loops. It's kind of like you go on like IGN or GameSpot or something like that, and you're looking for reviews on games, and it's just like, why is everything like a 9.5 out of 10? If something gets an 8.5 out of 10, it's considered bad. So it's kind of like our scale is on the upper end, because we're not intending on failing 50% of the students in the course. I think that would be a if I was to fail 50% of the students in the course, I think that would be a sign that I'm not teaching properly. What I'm looking for is that the vast majority of people, by the time I finish this course, understand the bits that I consider to be the main core of what you need to know in the course. So doing 1 out of 4 stages for 50% of the marks makes sense to me, because I would expect at least 75% of the students in the course to get 50% of the marks. So it's sort of, you know, I'm just fudging percentages here, right? But it's that kind of thing where, I mean, the worst failure rate I've ever seen for COMP1511 was about 20% of the course. I'm not sure if we just had a really tough term that time, but if that's the case, then that roughly equates to the fact that 20% of the course didn't do a quarter of the assignment, didn't do the first quarter of the assignment, I guess. It's, I'm just like, not a mathematician. I'm hand waving all this stuff. I'm gonna have a chat with Daniel Mansfield at some point, and we're gonna do a some kind of joint streaming stuff for people when we get a chance. We'll see how we go. Terry is asking, does that mean stage 3 and 4 are easier? No, definitely not. Stage 3 and 4 are the difference between a distinction, a high distinction, and a super high distinction trying to get 100 in the course. So obviously anyone who is shooting for the astronomically high marks like that, we're going to give the hardest stuff to. So we're going to expect you to do much more difficult things if you want to get those super high marks. It's like the challenge exercises. Like stage 4 is nearly like a challenge exercise rather than necessary. And I could say the same thing that I say about the labs. You don't actually have to attempt the challenges to pass the course. It's not necessary. The labs is different. You can get 100% in the labs without attempting the challenges. But the assignment is closer. It's not exactly, but it's closer to what your final mark in the course is likely to be. That's if you take a reasonable amount of time for it. If you spend 24 hours a day on it for the next 3 weeks, then you're going to get a higher mark in the assignment than necessarily you might expect for the whole course. But, you know, yeah. So stage 4 is like someone's already potentially looking at an HD in the course and they want to push right to the top of that. So it's super hard because of that. Oh, Shayek's saying jokes, we can do this week's test, so it has been released. Wait, Michael says it's due in 10 days? It shouldn't be due in 10 days. Because it's a weekly test. I will check whether I've got the due dates wrong on that. I'll have a quick look, but I'm pretty sure that I've got all this stuff set up to release automatically. Mason is telling me to scroll to the bottom. I'm not sure which thing. Oh, you asked a couple of times that the live stream tomorrow will be recorded. Yes, so it's just going to go up on my YouTube like normal, and I'll upload it to 1511. So to Moodle, the 1511 Moodle. Okay, so we were talking about the assignment, and we can move on. The weekly test is out. I will have a quick look at it to make sure it's due at the right time, because I know that the automatic release will probably make it due at 5 p.m. next Thursday, and I sure as hell do not want a deadline midway through the lecture. That is chicken feeding time, and we don't want you stressed during chicken feeding time. Chicken feeding time is there to reduce stress. Okay. Stage 4 looks freaky, Shake. Yes, it does. It does look kind of fun. I mean, that's me being mean, because I teach the course, so I know how to do everything, so it looks fun to me. So if it looks fun to me and it looks scary to you, that's probably pitched correctly for that level of difficulty for the assignment, especially because it's not necessary. Oh, Morgs Tototo said, how do we know when to introduce a new function? And that is an amazing question. Because knowing when to bring a new function in is something that is really hard to figure out for yourself until you've sort of learned about things and planned out how a program works and stuff. So for me, in this one, the 4 functions that I wrote were based on my thinking around the problem to begin with. So already, once I break down my larger problem into some parts, I can think that these things are kind of separate. So definitely reading in the numbers at input and printing them back out are 2 different things. 2 things that are for different purposes. So that's something that I would think about for separating into functions. Whether I separate things into smaller functions or not depends also on reuse. So if I have a particular function like the swap that might be used in multiple different things, then I'll write it on its own, and then maybe it gets used by 2 or 3 different other functions in the program. You don't know this for certain until you start to get a feel for it. It's a practice thing. So don't worry if you can't tell in the beginning how to decide which things should be functions. Sometimes the program will tell you. Like, it'll tell you in that you look at your code and it's really unreadable because it's gone so far along. It's so far indented and so far along that you can't read it anymore. And there's so many ifs and whiles inside each other that you don't understand where you are when you're in the program. That's a good place to take a chunk of that and put it in a function and say, all right, inside this if and this while, do this function. Sorry, chicken's just running across the room. She's doing zoomies. Yeah, so you can choose whether or not all that complexity of depth of indentation could be made less confusing by replacing several levels of it with just one word that says, okay, this function happens here, and then you'll find things start to become more readable. So we can do functions to separate work that the code needs to do into different things. We can also do functions to stop the code from getting too complex to read. Those are often the 2 reasons, and the other reason we might have functions is let's write a function because something's going to be repeated multiple times and we don't want to write the code multiple times. So those ideas are the things that are going to lead you to separate functions into different parts. I feel like what I just said then should go into the functions lecture. So I think in future editions of the course, I'm going to take your question, Morgs, and I'm probably going to put a slide in there because I think that's a really good question. Andrew is asking, does that mean the main function is declared in the standard io.h? I think you're asking about the stuff with includes and things like that. Let's go back to some code and look at that. Does this mean that this would have a declaration somewhere? It doesn't. It's the only function that doesn't. So all of these other functions might get used by something. The main never gets used by something else in the code. So we never call the main somewhere else. So I never have this, for example. Int x equals main, like that. I can't call main. Let's actually, this is a really good question. This is another good question. So who was asking that one? Andrew Thunderthief was asking this one. The main doesn't have one of these, and so Andrew was asking if it's declared in here or somewhere. It's actually not. It's the only one that isn't. It's the only one that only has a definition. But let's have a look at this and see what happens. Because what I'm expecting to happen here is my compiler is going to say, whoa, 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 you can't do this. Because if you think about this, if my main calls read inputs then calls my main, which calls read inputs calls my main, which calls read inputs, calls my main. I have an infinite growing, cascading, building up, calling of functions that never return. So let's see. I think my compiler is going to say, no, buddy, you can't call main inside your function, inside your program. I call main. The computer calls main when I run the program. You don't get to call main again. It happens once only. I'm going to assume it's going to say something like that. Ooh. Ooh. It's letting me do it. Let's run it. Let's run it and break stuff. Okay, so the only thing it's warning me about is that this variable that I'm taking from my main isn't being used anywhere else. That's a good warning. We want to think about that because we don't really want to create variables and never use them. That means that they're a waste of memory in that sense. But it's not worried about this main. So I think things are going to go very badly when I do this, but we'll see. Oh god. We broke stuff. Segmentation fault. We didn't even get a good error out of this. A segmentation fault is usually a memory error. I only know this from experience. This is not part of what I teach in COMP1511 because usually we don't get to a point where we break a program this badly. Segmentation fault, uninitialized variable access. I don't know where the uninitialized variable is coming from. I don't even know where the program got to. But I think that what it did, segmentation fault usually is a memory thing. So what it does is it creates the main and runs it, and it creates read inputs. So the main then creates one instance of read inputs, the function. Read inputs creates an instance of the main, the function, starts running it, creates the read inputs, creates the main, creates read inputs. Nothing ever reaches the end of its curly brackets to close, and so it's just opening more and more and more running instances of both main and read inputs. And so it got to the point where it used up all its memory and blew up. I think that's what happened, but I don't actually know. So I'm going to remove that now, but I think that was a cool experiment. Save that, and I'll go back to my... In case I want to run it again, I'll compile the old one. But that was pretty cool. That was interesting thinking about that. Yuji is asking, what's the use of pointers in the swap function again? The use of pointers was to say that this could get access to the variables themselves. So if I did this with just these, number A and B, and I didn't give the memory locations of these, I only gave the values of these, then swap nums would have no effect on the array, because swap nums here would have no access to anything that's in jumble. So it wouldn't have access to the array that's in jumble, which is also the array that's in main. So it wouldn't have access to that memory, it couldn't rewrite it, so it wouldn't be able to make changes. But if I just Control Z, which is to undo the changes I've made here, now if instead of giving the number that's here, I give its address, so I allow the swap nums function to get access to these particular variables, it now will create pointers aimed at those addresses, integer pointers A and B aimed at those addresses, which means it now has these pointers aimed at these two addresses here, which means it can make changes to them. If it had gone the other way, there'd be a 1 and an 8 in here, and it would make the changes between the two of them, and it would make no changes to these. That's why we're using pointers, to get us access back over there. Priya's asking if this is a typical use of pointers. I would say that this is an early use of pointers. So this is us saying, I would like to give some numbers to a function, and I don't want a single answer out of these. I want you to change the numbers that I've given you. So this is definitely one of the most simple uses of pointers, is to say, I just want to give access to something that I've got here. I want to give that access to some of my functions. So I want these functions to have access to this. For this example, it's actually in here. It's like, I've got this, and I want this to be rewritable in this function, but I want to give this function specific numbers. So I give it these two numbers, but instead of giving it just the numbers, I'm giving it the addresses so it can change things. Later on, we're going to see much more complex use of pointers. We're going to be following pointers into objects and stuff like that. We're going to use pointers to connect objects to each other, but not gonna go into that now. Too much to think about at once. There are already plenty of brains fried today, as it was. Masony has a problem. Oh, this is, you were trying to get me to scroll down to this earlier. I apologize. I hope you're still here. Oh, everyone was saying that the test was out. Yeah. Masony's asking when the assessment live stream is tomorrow. I've scheduled it for 4 p.m. I've put a link up in WebCMS. I think I made it public, so it should be visible. And I'm doing it over the same system, right? So it's just over the same YouTube Live. Nothing special, nothing different. I guess the only difference is that there's less slides. I might put some slides together. I still haven't decided. I do have some slides which will keep me on track for what I want to talk about for the assignment, but a lot of it will be more of this question and answer stuff. So it's kind of like the hour after the lectures that I keep doing for everyone, but a dedicated time for that with priority given to assignment questions. And yes, Masonry, I'm going to record it. So it'll be accessible not just on YouTube Live, but I will upload it to the Echo 360 as well. And Taylor's reminding me that the weekly test says it's due Monday, 5 p.m., which is definitely incorrect. I will go back and I'll check that. Eric is asking if I will teach COMP1521 next term. I apologize, I will not be teaching 1521 next term. As much as you might want me to just follow you personally through your degree, teaching you, I can't do that. That would break my brain, I think, if I had to teach a new subject every term. It takes a lot of time and effort to put a subject like this together. So all of that time and effort I use to deliver 1511 again, rather than, because you think about the turnaround in between terms, and all of the content that goes into the slides and the tutorials and the exercises and stuff. If I had like a week, I usually have less than a week. I have negative time usually. Term 1 was finished sometime around week 2 or 3, because it takes that long to wrap up all of the admin to finish a course. If in that time I had to also figure out what new content I was teaching and then teach it, that would be pretty painful. So apologies, Eric. You will have other teachers. Michael's asking, are we going to learn how to have things run at the same time, or at least simulate things happening simultaneously? Not in this course. In this course, we're doing the basics of learning how to get the programs working, not necessarily run two side by side. There's plenty of that later on, though. In later courses in CSE, there's a whole lot of stuff for concurrency and stuff. So if anyone else is wondering about this, this can be thought of as the idea of having like two mains running at the same time but separate, so they're both running and they're both poking into the same memory at the same time. We call it concurrency or threading or multiple processes and stuff like that. Like you will notice that like a lot of your the CPUs, the processors, not processors, that we use, we really need to rename them, will have multiple cores. So mine has, I think, 6 cores on it, which means it can run 6 different programs at the same time, which can be really, really confusing to your memory if they're sharing memory, like which one gets access to it first and stuff. And it's a huge field in computing, is just dealing with multiple programs running at the same time in the same space. Oh, Michael's saying in the assignment, if we have the blocks move down automatically instead of every time the correct input is read. The 1511 arcade is that. So the 1511 arcade, it's not necessarily concurrency, but it's got the ability to work in real time and do the blocks whether or not it gets the input. So if you want to, if you get to a certain point in the assignment, you can start playing around with the 1511 arcade. You didn't phrase the question poorly though, Michael, as you're saying them. Like, concurrency and threading is the thing that you're thinking about, which is totally fine. And you're welcome, Morgs. I've just gotten up to your message that you were thanking me for discussing your very interesting question about knowing which things get split off into functions and which don't. And Michael is saying, yes, you were talking about scanf seems to pause the program until the input is given. So yes, it does do that. It stops the program from continuing to the line after it until it finishes running. So until it can read something from the user, whether it's correct or not will change what it does. Will we learn how to have things continue while scanf waits for an input? Not really. In this course, it's just one line of execution, and if that line of execution is stopped, nothing else happens. So it just waits. Yeah. There are sort of ways to do it, but that gets into the realm of what we would call real-time programming. So stuff that can move in time and space, in a sense, as opposed to our programs, which are they're along a line of execution, and they go as fast as they possibly can until they're forced to stop, and then they go as fast as they possibly can. So as opposed to something that works in real time, which is like, okay, do a certain amount of work, let the user see what you're doing, then do a certain amount of work, that kind of thing. So very much what you have in games and interactive user interfaces and all that kind of stuff. That's very hard to do, and it's not something that we would try to throw on a beginner as an introductory program, like introductory course like 1511. We're much more interested in getting you up to speed on what we consider are the standard kind of ways of organizing information and ways of utilizing that information first, before you start thinking about how to do that in a way that a human can watch it happening in a time scale that humans can understand, which is much slower than computers. So no, we're not going to do that, but it is definitely available later on in CSE courses. Renana is asking, what is the purpose of having int outside the main void? I am not sure exactly what you mean by that, other than, say, this integer or these. These aren't actually created variables. These won't be created until the opening of the curly brackets that they have there. I'm not sure if you're wondering about creating an int outside, like this. This is what's called a global variable, where this variable is accessible from anything in this program. Now, it's like this is also outside, and it's accessible to anything inside this program. The danger here is that this thing can be changed by anything. So because it's not inside any of the curly brackets, it's not protected by any of the curly brackets. And so these things, people often use, like, this is a really old school thing. People used to use these things to pass information between different functions, because you could get one function to change this to something, and then the next function to read from it. But it's super dangerous because you don't know when it's been used, and it's just outside the flow. So it's just, it's like a renegade maverick variable. This is just could be what you want it to be, but it might not be, because you're not sure. If it's inside these and they get passed around as variables, then you're very sure about what's happening to them, because you know where they are at each point in time. This thing, you never know where it is because it's outside of everything, so it's super dangerous. I never use them. I learned my lesson years ago using a couple of those and just having my program blow up and not know how to do it, not know how to figure out what was going on, because these magic numbers could do anything. You know, they could get changed by any function. So it was, yeah, very dangerous. I suggest you never do it. In fact, I don't know if DCC will just be like, just don't do this, but it's definitely against the style guide, and you get, like, you lose all your style marks for that. Not even to mention the fact that whether or not you lose style marks, you're probably going to end up in a situation where you don't know what your code does if you use those, which is much worse than being a little bit unreadable. It's at the point where you literally won't be able to fix problems because you won't be able to understand what things are doing. So yeah, I don't even know if that's your question, but I thought it might be, so I thought I'd answer it that way. Okay, Freya is, Hong Freya, sorry, is saying, could you explain what that 2 means in line 67? Let's go to line 67. I think I know what this is going to be. It's going to be in the jumbler, isn't it? Yeah, random stuff. This is largely meaningless. So this is me trying to swap the integer in index I with another integer somewhere in the array at index j. So what I did was I just doubled the index, which is just moves. So I let me draw this for you. Oh, did I close paint? No, I didn't. I'm gonna make a new one. So here's my indexes of my array, and let me say I is equal to 1. Then what I'm going to do is, if I is here and equal to 1, I want to swap it with another one. But this was just me going, I just want to find another one. So I just said j is equal to I equals 2. So j is equal to I times 2. J is equal to 2. So it gives me this one, and it'll swap the values that are in here. So whatever this value is storing, whatever this value is storing. When I then becomes 2, oops, change my color. I becomes 2. J then is equal to I times 2. J then becomes 4. All this is doing is I is moving through the list. So I became 2. J became 4. All it's really doing is, for each I that I'm doing, it's finding a J somewhere for it to swap with. It's not important what it was. This code here, as I was saying, it does not have a particular reason. It's just a kind of random other index. So J is just a random other index that I've just made sure that it's between 0 and less than nums. But otherwise, it's just another another element of the array, so that I can do some swapping and mess it up. This is like me putting a deck of cards on the table and going but in code form, right? I was not doing this with a particular intention. It was just to mess things up. So hopefully that helps. Yes, cool, we got it. Oh, sorry, I see you changed your username there, so it's Freya. Okay. Liang Chao's asking, can I give an example of where we do the swap nums with just normal integers without pointers for comparison? We can't. That's the thing. Okay, so if I'm going to do this, let me just write another function. This is really hard to do, right? So we've got int a and int b, which means we've been given int a and int b, and we need to swap them. Okay, we could do something like this. It's really silly, but we could do this. Return b if we do int a and b. See, the thing is, I cannot change these values because me changing what's in a and b doesn't do anything, because these are created inside this function. So if I return b, then I could do something like here. There's really no point having that as a function now. Yeah, there's no function here. Nothing would work, because there's no way I can swap these things around. I can take one of them and output it, and that's the best I can do, because I only have one output, one integer. So I could say nums I is equal to swap ints nums I nums j, and that would take whatever was in nums j and now put it in nums I. The only problem is I've now lost what used to be in nums I, and I can't swap it back. So I would have to then go int temp is equal to that. And by that point, I should not even use this function, because once I've started doing this temp thing, then I might as well just do the code here. So temp is equal to nums I. Nums I is equal to nums j, because I've saved nums I into the temp, which means I can write over it with nums j, and then j is equal to the temp. So I've just moved my things around here. I can't, I've tried to put it in a function, but I can't. It doesn't work. So the only thing I could do is to literally do the swap code here, which is what I could do if I didn't want to use the swap nums function. But this is just annoying and confusing enough that if I call it swap nums, then no one has to read this ever. They just read this and it's easier. Alright, I'm going to revert that, because I don't want that there. I was like, I shouldn't have Control Z that actually. That's because there's just too much. Alright, I'll put this back and I'll say this function is unnecessary. So I'm going to get rid of that. Yeah, so I hope that gives you an idea of what's going on there. Is that the reason I picked swap nums as a function is it's actually impossible to have a function that swaps two numbers that are somewhere else in the code. There's no way it can access two. It needs to have two outputs to do that, and functions do not have two outputs. The whole way that they work is that the only thing that they can do is basically transform themselves into a single variable when they finish running. So having two pointers means I have access to two variables. So that is technically, if you think of it, a way that we can have two outputs for a function. Shayek's asking if it's possible to have too many constants in your code. You like labeling stuff with words and it's easier to understand the code, so you like having multiple constants that are still equal to 1. That's okay, and doable. I would be careful about having multiple constants that map to the same number. There's nothing wrong with it. It'll still work, but it could get confusing because you forget which one to use in which case. Having said that, if you do need multiple constants that are equal to the same number, you can still use that to make your code really readable. Because it's like, this constant is 4 and this other constant is 4. But they're used in very different contexts. They're not the same 4. So you could say, this 4 is the quantity of this thing. And this 4 is the number of times that this loop over here has to run. And they're different, so they're going to get different names, and they're going to go in the code as different names. I would consider that to be good code style, because you've definitely made your code more readable in that point. You've made it more understandable, so you can, rather than having the magic number 4 somewhere in there and you can't tell what it's going to do, that would help you a lot more. So yeah, I think, Shayak, you could definitely do that, but just be careful when they're mapped to the same number. You could cause issues. Not necessarily issues with the way it runs, it'll still run, but whether it's understandable is the thing. Liang Chao saying, I saw a YouTube video where he names every variable with one character so it compiles faster. Is that true? Technically, yes. But I think that it'd be interesting to write both of those bits of code and compile them, one with full variable names like this and one with single letters, and see what the difference is in compile time. Because, I mean, how long does it take to compile these programs? 1 second. How many seconds are you going to lose if all of your variables are single letters? I think that, yes, that person can do that if they want to, but the trick would be, if you're trying to save time, you want to make humans faster. The machines are plenty fast. Saving a few milliseconds on compile time, I don't think overall is going to save you that much time in being effective. And I would never suggest it while you're learning. I know that there are ways to speed up code, but even changing variable names, it doesn't. Yeah, speeding up compile time is also kind of irrelevant, because you compile a program once and then run it many times. You know, in a real production environment, is you compile it once, you ship it, and then it gets run thousands and thousands of times, right? So your runtime is important, but your compile time is not super significant. That's take that with a grain of salt. For some people it is. People working in massive interactive 3D environments tend to work on things that take, you know, half an hour to compile, and so then you might want to do it, but I still don't think variable names are actually going to save you very much time. So yeah, it is faster, but the time it takes a computer to read a single letter versus reading 10 letters, that's not the time that's important. That's not the time that's going to save you anything, really. Oh, so Priya was answering Renana's question, which maybe was that this was the int that you were asking about. Maybe I answered a different question, sorry. This is like the main is a function, and it has an integer because it's possible for the main to actually give back a value in the same way that read inputs gave back a value. That's why we have return 0. I didn't even put it here. Return 0 says that this is ended correctly. Yeah, Priya's explaining the whole thing. Sorry, I'm just talking over here. You know what you're doing. Zuckerberger is asking if WAM matters. Not a question for me to answer, I think. WAM matters to you depending on what you want to do with it. If you're looking for a program transfer, it matters. If you want to do honors, it matters. Certain companies will care about what it is. Other companies will care less about what it is and will be looking for a portfolio of work. Some companies are looking for particular personality traits first before they even look at your WAM. So, yeah. I don't know. Look. University is an artificial construct that might be entirely bullshit. Working for digital digits in a digital bank account might also be completely bullshit. So on the scale of things that are bullshit, WAM is definitely on the scale somewhere. One cannot measure a human being by a number and expect to get a good result out of that. There's heaps of people in this course who will have a low WAM, who will get really good jobs because they have a capacity to improve better than other students in the course who have a higher WAM than them. Maybe. But the people with a higher WAM might also have the same capacity to improve. So it's not... Yeah. I don't know. I know we get caught up on stuff like that a lot. But I don't think it's like super important. But up to you. You know. If you need it, then use it. If you're planning to go into research later, your uni marks will count for things. So if you're already thinking I'm going to do a PhD, then get high marks, because you need high marks to get like government support scholarships to do a PhD and that kind of thing, or even be accepted in. And if you want to get into honors, you need high marks for that kind of thing, unless you're in an engineering degree and you're in honors already. But otherwise, think about what you want to learn more than the WAM. I mean, it's easy if you want to just go for the WAM, because the WAM is like a rough indicator of how much you've learned. But if you learn things well enough to get marks and then you forget them really easily, then that's not as good as a deeper level of understanding of things and taking the time to learn things, knowing that maybe you're going to get less marks, but you're going to know things in a more thorough way. You know? Hard to say. I probably shouldn't have gone off that whole thing about the WAM, but I mean, like, you know, it's hard, right? Priya is saying, how does the jumble function use swap nums if it doesn't return anything? Yeah, good question. We're in the magic of pointers now. Swap nums does not return anything. Swap nums goes to these memory addresses and changes what they are. So, classic void function. A void function does not give back any information. So this does not give back any information to jumble. It has side effects. The side effects are whatever it does to these. Or other things, like printf has side effects that doesn't do anything to the variables, right? But it has side effects that end up being seen out here. So the side effects are the values at the end of these two pointers are changed. So if I give this locations, these addresses of these, it turns them into pointers here, and then it changes them. So it says, this gets the value that used to be there. This gets the value that is in here, which is the one that used to be there. So B gets A and A gets B. So swap nums does something because the pointers give it access to this array to change stuff. Okay, people should go. I should go as well. I stayed longer than I normally would have. I can't believe I stayed a whole hour after the lecture talking to people. But yes, I should wrap it up there. I think everyone's pretty tired now. 3 hours is probably shouldn't lecture for 3 hours. I mean, like, sure, the last hour is not really a lecture, but yeah. Hopefully that helps. Next week we will be playing around more with functions, and we will have some by next week I mean in your tutorials and labs next week we're going to look closer at what's going on with pointers and functions and stuff like that. So I will see everyone, well, however many of you are interested in an assignment live stream tomorrow afternoon. See you later.